All right. Share my screen. Yeah. Welcome everybody to CS-6515 office hours. Today I will be going over NP completeness, what it means to be NP complete, how do we prove something is NP complete, and why it's important. I will be covering also all the practice problems from week 9 and the NP complete problems from week 10, so that we can go over what the model solutions look like, why they are correct, and how you can use that to sort of write your own solutions. Keep in mind that this office hours will be recorded just like all the other ones, and it'll be shared with the rest of the class. So any questions you may ask, if you have your mic on, your video on, or in chat, it will be shared. Someone has their mic on, Trevor. I think you have a mechanical keyboard. Good on you. I love mechanical keyboards. All right. So NP theory is the idea that we are focused on polynomial runtimes. We care about things whether they are polynomial or they are not. Now, there are other types of problems or problem spaces that goes beyond just runtime. Some of them care about space. Some of them care about additional specifics about runtimes. But for the context of this class, when we talk about NP theory, we want to know if something is polynomial in runtime or not polynomial in runtime. And typically that becomes exponential or factorial. So O of n to the k for some constant k is considered to be a polynomial runtime. So anything that's based on n squared, n cubed, n to the fourth, we used to care about, specifically between, say, O of n versus O of n squared. But in this part of the class, we don't really care about that. We just want to know if something is within the polynomial runtime space. Okay. Then we have exponential runtimes, which is O to the k to the n, where k is some constant number greater than 1. So something like, O 2 to the n, or O 3 to the n, or O 4 to the n, what have you, or O of n to the n. Anything that goes to an exponential of the number that's representing your input size is considered an exponential runtime. So these are the two we really care about for this part of the class. But there are something called pseudo-polynomial runtimes. And this is, I think, one of the things that really confuse students and people getting into this space. So the way you want to consider pseudo-polynomial runtimes is this statement. It is polynomial to the magnitude of the input, but exponential to the size of the input. What does that mean? The magnitude of the input means what the input is representing as a number, okay? But the size that that input needs in order to hold that number doesn't get bigger. And so when you have a runtime that is polynomial to just the magnitude, what that number represents, it becomes exponential to the size of the input, because the size of the input does not need to grow necessarily with the growth of the magnitude. And I'll show that in as an example in a moment. P stands for polynomial. NP, so anything that runs in polynomial time is considered P. NP does not mean not polynomial. It means non-deterministic polynomial time. It's a really weird way to consider it. So if it takes a moment, that's fine. But what it means that if you had a way to know that basically exactly what steps to take in order to find a solution, like you have some magical way of knowing exactly what steps to take, then that kind of computer or that kind of system would cause that solution to be found in polynomial time. And I know that's like, why is that different than just saying not polynomial time? Because there are additional things that's beyond the NP space that's also not polynomial time, but has like different things about it that makes it also not considered NP. So non-deterministic polynomial time is if you had a special system that could always tell you the right answer, you could do it in polynomial time. But it can be verified in polynomial time. That's also the really important part about NP, is that you can take a problem and a solution, and you can check to see if it's a correct solution. Okay. Does P equal NP? So this magical computer that I talked about Is that possible? Is it possible to have a computer that knows to do the right things to get a polynomial time solution to such problems? Okay, and um, the other way to address this question is if we can verify a problem in polynomial time, can we also solve it in polynomial time? Okay. And is this true for all problems that are in both of these spaces? Okay. And so this is one of the really I think it's called like the millennium problems, where it's like really difficult to solve because um, intuitively you would think that P does not equal NP, but it turns out proving such a thing is just as hard as proving the other direction. So we haven't been able to prove it one way or another. So normally when we say, a problem is not P or not polynomial, we try to correctly say it by saying it is not known to be polynomial, which is to say we don't know if it's polynomial or not, but we don't have a polynomial solution, and therefore it's not in the space P, not known to be in the space P. Okay, and this class of problems, if you can prove one of them is polynomial, it turns out that the entire class of that problem, the NP complete and NP hard problem, collapses into the polynomial space, which is really cool. Okay, pseudo polynomial runtimes. Why is this interesting? So knapsack is a known pseudo polynomial problem. We know it to be the solution to be pseudo polynomial. We don't have a polynomial time solution for it. So this runtime is O of n times b, right? So for Fulkerson is O m times big C, which is the capacity of your fluid network. So this is also a pseudo polynomial runtime. Now, be careful here because Edmund Karp's is a polynomial runtime. So the problem of max flow is known to be polynomial. But specifically, the Fulkerson solution itself is pseudo polynomial. Okay. So if n and m are based on the size of inputs, let's say n objects and m edges, okay, a runtime based on n and m would be considered a polynomial runtime. Okay. But because B and C are magnitudes, these are just numbers. They represent a number. They don't represent a input size. Therefore, they're not part of the polynomial space. Okay, they're a single number that increases the runtime without needing more space, right? Because our runtime is relative to the space of the inputs. So if the magnitude increases without increasing the space, then our runtime no longer is considered polynomial. Okay. And here's a pretty good example. Hopefully this gets the point across, and you students will no longer be confused. So suppose n is represented by two 32-bit numbers. Okay, so one item is 32 plus 32, which is 64 bits, right? So this is your representation, right? Your two items then goes up by 2 times that, which is 128 bits, and so forth, right? Every time you have one more item, your number of bits increases. Now, it doesn't mean that it increases like, linearly exactly, but it increases by a sort of, predetermined amount that like, if I tell you, if I go from n to 2n, and you don't know what n is, you have no idea what the number n is, you can just confidently say, okay, yeah, it'll take about double that space to represent 2n. That's fine, right? But with the number, if I tell you that b, and I go, oh, 2 times b,
Sorry,
you don't
Joves.
know. Yep.
There's a couple people asking, can you go back to the previous slides? It's been asked like maybe 3 or 4 times.
Okay, sorry. This one?
I think so, yeah.
Okay. Yeah.
Because I think it was Lee and Minnatullah who asked to go back to the previous slide. I don't know why though.
Okay. Does anybody questions on this slide before I move on? Or you just need to take a snapshot, which is fine.
I think it might be a snapshot thing.
All right, cool. No problem. All right. So if I was to give you a number and I just say, okay, double it, how much space does it take? You don't know. It really depends on how much. I mean, you can tell me it takes 1 bit, but if I tell you, what is the relationship between B and 2B as, a ratio of space, you don't know because it depends on where that number is, right? So it's not the same, right? So if I take 1 bit to represent 1 and 2 bits to represent 2, 3, I can still represent in 2 bits. 4, I can represent in 3 bits. Now, there is a steady climb, and so in the very beginning, it kind of looks like, oh, this might be sort of like the same as polynomial. But as that number gets bigger and bigger, your bit starts to represent more and more numbers, right? It takes 4 numbers before we move to the next bit, right? And so as we do this, right, you get all the way to 16 before you get to 5 bits, right? And this is 16x the first bit that you use to represent 1. But it only takes 5x space to represent that. And because of this, you're not getting a runtime that is polynomial to the space of the actual representation of the number. You're getting a runtime that's polynomial to the magnitude of this number, but it's actually exponential to the size of the number. And so in these cases, we call it pseudo polynomial. Okay, and a x is represented by log base 2 x bits. Okay, and so pseudo polynomial runtimes again is polynomial to the magnitude of the input, but exponential to the size of the input. Okay, and it turns out the
Joves,
reverse is also.
I
I'm
had
going to
one
finish
question.
this slide.
Okay,
I'm
sure.
going to finish the slide in it. Yeah. The reverse is true. So any runtime based on log of some number, so like as long as your runtime is considered log of the input, it is considered polynomial. And this is really important. Regardless of how B is represented, the second you are able to you get a runtime of log based on it, it becomes polynomial. Okay. But I guess that's not true. I guess you could have something like 2 to the n to the n to the n, and because of like this rocketing trajectory of exponentials, it becomes the log will remove one level of this. So you would need like log to remove all this. But in general, if you have a input size that is exponential, taking the log of this turns it into a polynomial time approach. Okay, and we'll see that in one of the problems that we're gonna work on. Okay, yeah, question?
Yeah,
I think
I had. Oh, sorry, I was the one that kind of interrupted in the middle, so I was just gonna. I had one question that's maybe. I don't need to confuse the conversation if it's just going to do that. In the book, it mentioned if there was a unary representation of a number that it it called it unary knapsack, and that unary knapsack would be uh, a polynomial algorithm because I guess the magnitude scales with the representation, the bit representation. Is that right?
yep.
Okay.
Yeah. So like if you did something
It was hard to wrap
strange,
my
like
mind around.
yeah. So the idea is that if you were to represent your weight or your budget, right, as units that you allocate space for. So if you had a B stands for budget of like 1 million, you actually take up 1 million bits to represent that 1 million. Yeah, that would be a polynomial time problem. So, and you can do that across any of these pseudo polynomial problems. Is that you take their representation of the number and you purposely use up space to represent it. Then that solution would be considered polynomial. Now, in your mind, you're thinking, oh, well, if I could do that with knapsack, that means I can turn knapsack into a polynomial problem. And therefore, if I can say knapsack is polynomial, all NP complete problems are polynomial, right? That's a fair sort of like, thing to ask. And then the problem becomes, well, you have this representation of knapsack, which, is called the unary knapsack problem. Can you reduce, right, from unary knapsack to the normal knapsack problem in polynomial time? And if you can't do that, then you have not collapsed the pseudo polynomial version of knapsack into the polynomial version of knapsack, and therefore you have not proven P equals NP in any way.
Okay.
Yeah,
I think that's the
yeah,
part that like I was like, well, how does this not just solve everything? Okay. That last
yep.
part is like the thing that has clarified it for me. Thank you.
Yeah, you can cheat, but you have to be able to cheat in both directions. And if you can't cheat in both directions, it's not good enough. Yep. All right. I don't know who has. I'm going to just try to call names. Anjanatha?
Hi, Joves. So regarding the Ford Fulkersons, you were talking, it's a, I think we went through that in the past, but a question about like, pseudo polynomial. So I know it's a framework that Ford Fulkerson provides, but in the lectures, we see that it is using the BFS versus the Edmund Karp using the DFS. And Ford Fulkerson increases the flow one by one at every edge. Because of that, it is pseudo-polynomial versus the Edmund Karp uses the min capacity across the path that it finds. Because of that, the Edmund Karp is polynomial.
So not quite. The reason why Ford Fulkerson is the way it is because using DFS, you don't find the shortest path. And because you don't find the shortest path, you will always increase your capacity, but you don't eliminate edges. You increase the capacity and it could continuously find routes. As you starve out the capacity of the edges is when you start to eliminate the edges. So because of that, using DFS, which is what you assume Ford Fulkerson is doing, ends up being a runtime tied to capacity. Whereas with BFS, what you're doing is you're finding the shortest path, so the least amount of edges in order to push more flow in. And by focusing on the edges, the least amount of edges instead, you start to eliminate edges from being considered. And so because of that, the runtime is based on the elimination of edges, and therefore it is tied to the number of edges that exist on the graph, and therefore that runtime is tied to the edges. Now, one of the coolest things that Ford Fulkerson and Edmund Karp teaches us is that although you classify solutions into problem spaces like polynomial, pseudo-polynomial, exponential, depending on the input, it doesn't always say that one is faster than other. It tells us one is a higher complexity level or higher complexity tier. But it's not like there's no gray area that the two can't overlap and say, oh, for some cases, this solution is faster, and so for some cases, this solution is faster. So that's just how it works out.
Thank you.
Okay. Equin?
Hi, Joves. Can you hear me okay?
Yes.
So I'm always struggling to understand the pseudo polynomial. So I'm wondering, can you give us like a example on actually it's polynomial to the magnitude of the input, but exponential to the size of the input? Or is there an say example coming later?
No, I mean the two problems I present. I mean the most classic example is knapsack, right? So like if I have 100 items that I want to fit, and I make it 200 items. If you just consider that part alone, right, going from 100 items to 200 items, and those items are represented by some 32-bit number, right? The number of bits I need to represent 100 items to 200 items is double. It's exactly double. If I want to go from 200 to 400, it's also double. It's exactly double. So for any given n, if I want to double the number of inputs, it's going to double the size of your the runtime. It's going to double the runtime, right? Going from n to 2n doubles the size it takes to represent that input, and it also doubles the runtime. So that is your polynomial runtime. It is linear, or in some polynomial increase of runtime to the increase of your input. When you take the budget into account, right? If I go from if I go from each of these numbers, when I go, let's say I go from 1 is representing 1 bit, right? So that's that takes 1 additional bit to represent. So going from 1 to 2, I double my runtime, right? Because it's O of n times b, and if b doubles, then that means the entire runtime doubles. Going from 1 to 2 doubles the size of just my budget to number. It also doubles the input size of that number. It also doubles the runtime. So that makes sense, right? That's what you intuitively think, happens for polynomial type runtimes. Going from let's say 2 to 3, you've gone up by 50%. Your input size hasn't changed, and your runtime actually also doesn't change. I'm sorry, your runtime does change. Your runtime is based on that. So your runtime goes up by 50%. Your input size has not increased, right? Going from 1 all the way to 15 or 16, okay? My input size has gone up 5x, but my runtime has gone up 16x, right? It's going up at an exponential level. So as your input size gets bigger, your runtime starts to get bigger faster because it's exponential, and that's what's the key marker of a pseudo polynomial runtime, is that as your input size gets bigger, your runtime does not get bigger at the same rate. It gets bigger faster.
Okay, I think this is the key you pointed out. It's faster than the inputs are growing. Okay, I got it now. Thank you.
Right. Now, it's super obvious when you have a true exponential runtime, right? O of 2 to the n. As n gets bigger, your runtime is exponential. That's really, really easy to see, right? So it's like clearly exponential. It's these big magnitudes that's kind of, a little bit more difficult because there's no exponential to this. There's no exponent to this b. But you have to understand that as this number gets bigger, your runtime is still growing exponentially, even without an exponent. And that's what makes a pseudo polynomial. Right? And why? So the other question is, you come from the other direction. Why don't we just call it exponential? Why do we call it pseudo polynomial? Right? And that's a good point. We could have just called this exponential because it is technically exponential. The runtime is exponential to the input size, but it's just it can be confusing. Like, oh, but there's no exponent here, so why is this called exponential? So then we call it pseudo polynomial. It's just like a way to describe it. Manjunatha?
Joe, sorry. Yeah, thanks for taking the question. Follow up on this. So when you converted that pseudo polynomial into polynomial by making it a search problem, going from 1, 2, 3, and so on. So that is a polynomial runtime. Is this concept is only applicable for pseudo polynomials, but or it can also be applicable for the NP problems, where if you convert that into a search problem, it automatically becomes a polynomial runtime?
No, it does not apply to these. I'll go over what the difference between decision and search problems are. But for the sake of just pseudo polynomial, just understand that this number right here, as this number goes up, your runtime goes up faster. That's that's the key takeaway from pseudo polynomial, is that for polynomial problems, as the input size goes up, your runtime goes up at the same rate each time. Now it can go up, n to the fifth or whatever, but it's still going to go up at the same rate. Okay. For exponential problems, you have where the input goes up some size, but the runtime goes up, it skyrockets. It goes up at a faster rate. And for pseudo polynomials, it actually fits this pattern, even though it looks like it would fit this pattern. It doesn't. It fits this pattern instead, where the input sizes go up and the runtime starts to skyrocket because it's exponential.
Thank you.
Mahmoud?
Yeah, I don't know. It's just not clicking with me. I can't seem to wrap my head around why, like, if in this particular case you have O of NB, which is not polynomial, pseudo polynomial, and it's because of the bit representation, how when you're adding one number to it, it tries to it expands number of bits, and it could just increase it exponentially. I kind of get that, but how is that different from doing something like if you're trying to do a runtime of O of NM in some of the graph problems that we had before?
Yeah.
Why are we treating M in the same way.
That's fair. Let's grab. Excuse me while I grab some sets. All right. So if we have O of n, oops, that's not what I want. Okay, so if we have O of n, why is this so thick? So that's okay. Well, if you have n and n, right? So this is O of 2n, right? Oh, actually, that's bad. Let's do O of n m. All right, so O of n times m, okay?
Yeah.
Right? All right. That's our runtime.
Sure.
Okay? Okay. Let's just make it simple, okay? For n and m, every time it goes up, we are going to represent the number by one more bit. Okay? Let's pretend this is some single bit object. Okay?
Okay.
You need to know whether it's ones or zeros, right? So let's just say that ones or zeros, okay?
Mm-hmm.
So what is the runtime here if n equals 5 and m equals 100? That's your
500?
question. There you go. Okay, we got 500. Okay, so that is our runtime. What is the size? So we have n and we have m, right?
Mm-hmm.
And we want to know what the sizes are to represent this, right? So if each one is a bit, what is our size to represent these two numbers?
2 to the 5th and 2 to the 100th.
Well, we're just going to say it's one bit, right? So it's going to be 105. So we have 105 bits to represent a whole bunch of ones and zeros.
Oh,
Okay?
sorry. Okay, yes.
Yep.
Mhm.
So that's fair, right?
Mhm.
Now, similarly, if we took this and we did O of n b, okay? Now, we say that n is the same thing, okay? N is still represented by a single bit, right?
Sure.
And we want b, right, now to be represented by its bit representation. How many bits does it take? Okay. So now we have n equals 5. Okay. And b equals 100. Okay. This is still going to be O of 500, right? Our runtime has not changed. We agree
Sure.
to that?
Yeah. Okay.
Okay.
Yeah.
Our size now, though, is equal to 5 plus what's log 100? With 128, so 8. So like 7, right? But
It's
we
under
have to
7.
right. So 7, right? Because you have to have enough to represent, right? So this
Sure.
is now 5 plus 7. So this is 12, right?
Mm-hmm.
Okay. So we already can see right here that our size to runtime representation is tiny compared to 105, right? 105 to 500 is a different ratio than 12 to 500, right?
Sure.
Now, this difference in how much less space it takes to represent the numbers that we are trying to get to versus the number of inputs that we are trying to get to becomes even more pronounced as those numbers get bigger. So if we go the other direction, let's say, n equals 100, right? M equals 100, okay? So this is now O of 10,000,
10,000.
right? Okay. Our S, though, is 200, right? Now, if we did this one, we have n equals 100. Okay. This one's so you still have this O of 10,000, but notice here that my B hasn't changed, but my N has gone up. So it's actually okay. Oops. So when I adjust the size of the actual the part of the input that's not a magnitude, I can see that my runtime is kind of getting closer to it, right? It's kind of like, okay, that's cool. I can see my adjustments are making my runtime kind of go up. But if I flip it around and I say, okay, well, if my n is equal to 5 still, but my b is equal to 2,000. Okay, my runtime is still 10,000, right? But now s is equal to 5 plus
11?
is it 11? Yes, it
I
is
think
11.
so.
Notice how when I have two inputs that's actually representing bits, my runtime goes up, pretty my runtime in my size, right, goes up at about the same rate, right? It's not it's still like it's still like it's not linear. It still goes up faster than the rate of growth, but it's not like this like huge jump. Now on the bottom part, if I have two different numbers. I have one that's representative of input size and one representative magnitude. Whenever I increase b, my input size is not growing, not much, right? Not much at all.
Mm-hmm.
But when I increase n, my same runtime, my size does grow, right? Therefore, this runtime right here, right, is polynomial to the n, but not polynomial, and it's polynomial to the magnitude of this number, but it's not polynomial to the size of this number, right? So you get this like exponential growth, even though your b here doesn't have an exponent to it.
But why are we considering B as non-bits, like a non-bit version, while M is its bit representation? Why are we
Right.
cherry
Right.
picking this?
So if n gives me information on about the items I'm considering, right? I told you that n is 1 bit representing ones and zeros. M
Sure.
is also 1 bit representing ones and zeros.
Yeah.
Down here, n is 1 bit representing ones and zeros, right?
Yeah.
B here is a number that's represented cumulatively by the ones and zeros that I need to represent this number. I need far less space to represent this number than I need to represent this thing going up.
Mm-hmm.
Right. So the fact that I need far less space to represent this, as the space grows, the runtime here grows exponentially. Because your runtime is some relationship to your input size.
Mm-hmm.
Right. So when this number grows really, really, really quickly, my representation of that number going from say 7 to 11, going from 100 to 2000, does not grow very quickly. And so your runtime becomes exponential to the size of the input.
I think I need to rewatch it. I'm not going to take up any more time. I feel really bad that I've taken up this long. So if I still have any questions, I'll post it. But I need to.
Right.
I think I just need to watch it over and over again.
Consider how many bits it takes to represents the actual contents of a document, the actual the actual words of a document. Okay, it takes up a lot of bits. But if I just needed a word count, right, and my word count is is just some number. It takes very few bits. I don't have any information about the document itself. All I know is the word count, right?
Sure.
So if I have runtime based, solely on the runtime, it takes so few bits to give me that word count that my runtime becomes exponential to the side to the number of bits to represent that word count. But if I had a runtime that actually needs the contents of that document, as the document gets bigger and bigger, my runtime gets bigger with it, but it's some polynomial relationship where on just the word count itself, it grows exponentially to the word count because there's such few bits that represent that document.
It's still not clicking, but I think I'm just not. I don't want to take up any more time on this. So thank you, Jovis.
Okay, no problem. Vikesh?
Yeah, so maybe I can reiterate, my understanding. So B is basically, it could be represented as 2 to the power k, right? Where k is basically
Yeah.
7 in this example. So when you
Right.
say 2 to the power k, it is basically n into 2 to the power k, and that's why it's not polynomial. It's exponential in k, which is what the
Sure.
input size is.
Sure. Yeah.
And
Maybe that helps. Maybe we say this is equal to O of n times times 2 to some k.
yeah, and then
And
we don't do that
yeah.
with And we don't do that with N, we do that with B
Right.
because when we say N, let's say 100 nodes, we are actually passing the nodes one by one. So our
Right.
input is a length of nodes, 100 nodes, A,
Yeah.
B, C, D, whatever. But B is a number. It's just a number. It's
Yeah.
not the actual.
Right.
So that's why we
Right.
cannot do that with N.
Yeah. So let's say n, the runtime is broken down to n times 2 to some k, where k is a non-constant. And because of that, because the 2 to k, it's now very easy to see that B here is going to create an exponential growth. Let's not tie the runtime to B, but tie the runtime to n times 2k. Okay. So as k grows, you're getting an exponential growth of your runtime on your based on your B's representation. Maybe that helps. If not, then we can try again next during the next office hours. Maybe it'll take a week to sort of digest, and then we can try it. Okay. All right. Let's go back to the slides. All right. Okay. So these are NP complete reductions. I apologize for missing last week's office hours due to travel, but hopefully there was enough in the threads and the other TAs answering questions that you were able to do this. So when we talk about NP complete reductions, what we're trying to say is, okay, well, we're giving some algorithm B or an unknown algorithm, black box algorithm B. I'm saying, okay, if I had a black box that can solve the problem for B, how do I reduce to it? I want to reduce my problem A to a such that algorithm B can solve the problem for me. So we have some transformation function here that an instance of A comes in, we do a transformation, it becomes a input to the algorithm for B, we put that in, and then we come out, we say, okay, well, if B has a solution, we now do this output transformation that gives us a solution to A. And if B has no solution, then it also has no solution to A. Now, this is important. You have to make sure that any and all solutions to B maps to a solution for your input. And that if B has no solution, you also cannot have a solution to A. Okay? Because if B has a solution for when A shouldn't have a solution, then you're not really sure what to do here. You're not really sure how your output transformation can determine whether a solution to B is or is not a solution to A. So a no solution has to map to no solution, and a solution has to map to a output transformation to A. So that's how reductions work. Okay, A is considered your known your known problem. This is a set of problems that we have given you that says these are the problems that you should know are NP complete. They have been definitively proven to be NP complete by someone, and therefore you are using these as your set of black boxes. B is your unknown problem. Now, you can, if you try to argue like, well, someone out there has already proven it to you. In the context of this class and the problem we give you on either homework or an exam, you have to treat the problem we give you as a unknown complexity. They're going to be NP complete. We're not going to give you a problem that's like, this is not NP complete, prove that it is or it isn't, and aha, gotcha. It is going, the problem we give you on the exam and on homework problems is an NP complete problem that we know of, but we want you to prove to us that it is NP complete. So you want to write the transformation f. So this is your input transformation function, and you want to write the output transformation. This is your output transformation function. Okay, so this is what you're trying to do. All right. So when you do these reductions, you want to go from A to B, or known to new, known to unknown, proved to unproved. There's a series of ways for you to remember this. The problem that you pick to the problem that we give you, proven NP complete to what you are proving to be NP complete, and so forth and so forth. A wrong direction proof, which is that going from B to A or new to known or the other direction. If you go in the wrong direction, there is a flat -16 reduction. Okay, and that -16, the entire reduction part of the solution is 16 points. You will lose all the points to the reduction portion of it. There is a proof that this problem is in NP that is graded separately, but the reduction part is 16 points. And if you mess this up, you're just going to lose all the points. I'm not trying to like tease you or make fun of you. I just want to make this as clear as possible. There is no coming back from this. There is no arguing on the point value. There is no arguing like, oh, well, if I had proven it correctly, this would work. It doesn't work like that. So there's a couple of reasons for this. One, the two problems that you are going to use, the one that you are using as a black box, and the problem that we presented are both going to be NP complete, right? We're not going to give you a problem that's NP complete. So yes, they can be reduced to each other in either direction. That's the nature of how NP complete works. If a problem is NP complete, it can be reduced to any number of NP complete problems, or all of them, right? So it's going to work, but it's not a valid proof. The second thing is you can always make a problem harder. Making an easy problem, reducing it to a harder problem doesn't do anything. You can say that, addition is as hard as multiplication if you throw a multiplication in there. Like that's not like, telling us anything about the difficulty of the problem. So going the wrong direction is really, really bad. And if you take anything away from this slide, don't do reduction in the wrong direction. Okay? All right. And there's no point in arguing this. This is a standard penalty that every TA will have access to. Okay. Any questions about the direction of the reduction? Okay, Amit?
Yes, good afternoon. I do have a question. I don't understand, like, we go from the known problem to the unknown problem, but maybe for like my intuition or understanding, can you talk a little bit more about why we go this direction? Because my instinct when I see an unknown problem is to convert it to a known black box,
right,
and then later convert the solution.
Right. So I think it comes down to an understanding of what a NP reduction is trying to do and why it's not like a standard reduction, right? So generally, you are saying, I have a problem. I have a problem I am trying to solve, right? I don't know how to solve this problem, right? And you're saying, well, if I had an algorithm or some library that I can make use of, like in a in a programming language, if I have some Python library that I can make use of as a black box, I can solve my problem, right? And so you're saying, okay, I don't know how to solve this problem. I know that this black box will solve the problem for me. Therefore, this is what I do. And this is a standard reduction. This is what you did in graphic, right? You took a problem that we gave you, you used one of the black boxes, and you took that and you solved the problem, and therefore you did it. Now, what that also means when you do it is that the black box that you used, right, in any given problem is going to be is going to be no easier than your original problem, right? Your problem cannot have a lower runtime than this black box, correct? If this has a known runtime, then your over runtime could be greater than this, right? But it can't be less than this. Okay?
Yes.
Okay, so that's great. So you're floored by the dice source black box I used, right? So this is your runtime. Okay. What we want you to do is we want you to take this unknown problem that we have. Do we call it B? Yeah. This black box is now B, right? And we want you to take a known problem A, and we want you to reduce this and get a right solution. Without knowing what the black box does, we can still infer the runtime relationship that we did previously. We're not trying to solve the problem, not really. We're just trying to prove the runtimes. I have said that this now becomes your floor of a runtime, right? You cannot get a faster runtime than this, right?
Yep.
Okay. Okay. Now, if I am able to take a polynomial reduction from this solution, and I can get to this solution, and then I get this runtime, right? I now know that my reduction is polynomial, some polynomial runtime. This has some unknown runtime, right? And my claim is that this runtime, right, will be still all of whatever A's runtime is, right? Because, and here's the thing, if this is a faster runtime, if I have shown that this can be a faster runtime, and I can go from A to B in a polynomial and some faster runtime than A, then I am claiming that I have found a polynomial solution to A. And that very much could happen, right? Like someone could potentially one day find some magical B problem and prove that A can be done in polynomial time. But we haven't found that answer, right? So my gut, or decades, maybe even centuries of proofs have told me that this is probably going to be some really high runtime. And so if I can reduce from here to here and still get that really high runtime, then this question mark becomes some variation of OA runtime, which means that this is also NP complete. So it's a really different reduction, and I understand this to be like really a really weird approach. But you're just trying to prove that this question mark of a runtime is also a really hard runtime, and by doing this reduction, it works. Now, what happens if I go the other way? So if I go B to some A, right? And I go, okay, I have a known runtime to this, or a known hard runtime. And I get this, and I say, okay, this is a known hard runtime. But because we know that this is always going to be the minimal runtime of this reduction, this continues to be a question mark. This could have been a really simple runtime. I don't know. I use a really hard black box to solve it. This could have been a really hard runtime. I don't know. I use a really hard black box to solve it. My runtime is based on my really hard black box. It's not based on anything I know about this problem. I can't deduce anything about this runtime because I passed it through a really hard black box. Whereas I'm saying here, I'm not saying that B is really hard or really easy. I'm saying because I know that I don't know what this runtime is, and I know that there has been no proven runtime, a proven polynomial runtime, I can guess that this is going to be a really hard runtime, and I can guess that I know this is a really hard runtime. So if I can do this reduction, I'm saying that this runtime is no better than this runtime. And if this runtime is no better than this runtime, and I know this is really hard problem, then this is also a really hard problem. Now, if I can somehow prove that this is really easy problem, this actually also becomes a really easy problem. So then the trick is find some B that actually can be proven to be really, really easy and reduce A to it. In the meantime, I can use this reduction to see if B is just as hard as A. And if B is just as hard as A, then I've proven that it's an NP complete problem. Does that make sense? That's why you do
that makes sense.
that way. Okay.
Yep.
Great.
Thank you very much. Yes.
Great. I got one today. That's good. All right. All right. So what do you need to do to write NP complete proofs? This should have been a post already done, but let's just go over it. So we give you a problem B, and you need to prove that it's NP complete. Proving things are NP complete is actually two separate things you have to prove. You have to, okay. So you want to pick a problem A to reduce to B. First, you need to demonstrate that B is in the class NP. Okay, that means that gives the steps on how to verify candidate solution B in polynomial time. So NP hard are problems that are considered to be hard problems. NP complete are problems that are considered to be hard problems but can be verified in polynomial time. Okay, so this is the first part to it. This proves that this is in the class NP. Okay, you must prove all requirements. So you don't know that we're giving you a working solution or not, right? You can't assume that the solution we give you is a correct solution, okay? But you don't need to prove a junk solution. If I told you, the solution is a array of letters, prove that is, verify that is the right solution. You don't have to go, well, verify that the input is a letter and not a number. Verify that I have an array and not a tuple or something, right? We're not going to give you a junk solution. We're going to give you a solution that follows the format that we claim, but you have to prove all the requirements. Okay. You may assume the candidate solution is a valid form for a solution. So correct data types, variable vertices, etc., are consistent with the original input. So we're not going to give you like additional letters or additional numbers that's not consistent with the original input. Okay. You must do this in all give a runtime. You must tell us what the runtime of this step is. And saying this is polynomial is not enough. We need an exact big O runtime. Okay. You technically can say this is constant because constant maps exactly to a single runtime, which is O of 1. So we understand this. I would still avoid this because then you kind of forget, oh, can I say this is constant? Can I say this is polynomial? Just go with this. I just want to point this out because some students ask. So you should not do it in terms of K, B, or G unless you bind it. What does that mean? So when the problem is said, okay, we have some n vertices, okay, and we want to make sure that we find some pattern, click, independent set, vertex, cover, what have you, and we want it to be within K target, okay? Most verifications or transformations can be done in O of K, right? Because once you have reached your target, you no longer need to keep looking, okay? And so students will correctly assume that K is less than or equal to n vertices, right? Doesn't really make sense if K is bigger, right? And they'll give a runtime in O of K, which is correct, except it's not polynomial. K here is a number. K here would make this solution pseudo-polynomial. We understand that K is less than n, less than equal to n. We understand that O of K would be optimal to O of n, but we don't care about that. We're not proving things are optimal or not. We're proving if things are polynomial or not. And O of K runtime is not a polynomial runtime because K represents a magnitude. Now, what you can also say is, well, O of K where K less than equal to n. Okay, this is what we call binding. We have bound the size of K to be less than or equal to n. And since n is an actual input size, O of K being bound to less than or equal to n makes O of k less than or equal to O of n, which is allowed. I still don't suggest doing this because you don't have to. You could just easily say O of n, and that works. You can say, I'm looking for this many vertices, and it takes O of n because I only have n vertices to count. And that's much easier and error-free. You're not going to accidentally forget to write down the right information to bind k to n. I would just go with O of n. But for the sake of completion and understanding of why you can't bind something to O of k, O of b, O of g, I wanted to share that. So can be as slow as you want, as long as it's polynomial. We don't no longer care about optimal solutions. We care about whether it's polynomial or not. That's the only thing we want. And it still has to be accurate. You have to give a correct runtime. But if it's polynomial, you're fine. Okay? Correct is much more important than fast, as long as it's polynomial. So as long as you can get to a polynomial runtime, give the easiest solution you can write. If you're coming up with optimal solutions on these things, and it's really difficult for you to get the idea across, stop. Just write the really, really simple, obvious answer that takes longer to do, as long as it's polynomial, and you'll get more points that way. Making a mistake on a transformation or verification step in order to get a more optimal runtime is points you'll lose, and it feels really bad. This is where this is one of the worst feelings when you see your grade and you go, oh, I could have just wrote the easier answer and gotten full points. And you cannot argue that with the TAs. TAs are not going to give you more points for a complicated optimal solution. And you arguing, well, that person's solutions is easy in brute force. The point of this part of the class is to write polynomial steps, and if you mess up, you're gonna mess up. All right. Questions about this, Mahmoud?
So, bit of a stupid question here, but there was a question, like for example, in the book, and I know we're going to cover them, but just to help get the point across, where you had to find like a subgraph that's at least size, let's just say G, and so it's okay for us to write O of n because, like you're saying, G is at most n. So there's no need to like reduce it to the smaller component because there's always something larger that it could be, or
Yep. Because G can be n, right? And that's okay.
G can be n. Okay.
Right. G can be as high as n, right? And so it's fine.
Now, okay, I guess that makes sense. Thank you.
Yeah. For those of you that are going to bring up the trauma of exam 1, it's not the same topic. It's not the same thing. You're not doing the same thing. So that's why you can say O of n. It's fine. Okay. A student asked, and I want to make this on recording because it's really important. Can you assume that the solution is the correct size? So if you have target K, can you assume that your solution is of size K? You cannot make that assumption. That is something that you are required to check. Any sort of requirement, not based on like, input verification, like validation, anything that's a requirement, like I need to meet this target, I need to be a click, I need to have this, I need to be satisfied. All of those are things you need to verify explicitly. If you miss it, you'll lose points. Bing?
Hey, Travis, I've got a few questions. So first of all, you just mentioned about the candidate solution size. I know we cannot assume it's of the correct size, but can we assume it's of polynomial size to the input? For example, it's not exponential size, meaning if I iterate through every element to check its size, it's going to be exponential time already. Like, for example, if you want to check the solution S size is, say, K or greater, the solution size is not going to be exponential to n, for example, 2 to the power of n, because that would by itself exceed the polynomial time, right? Just iterating through all the elements in the candidate solution. Because if you can give me an arbitrary candidate solution that's, terabytes of bits long. Just checking how long would take. That's no longer polynomial to the input.
You're not gonna. So you're not gonna get like a junk solution, like I said, right? So like if I give you a solution that is like, you know, a solution to an input, that solution would probably be polynomial to the input. So
okay, so we can assume that in addition to the type syntax being valid, basically,
yeah, like
when we
if
give
you
it,
if you assume, if you're looking for, if I'm asking you for the vertices to a click, you can assume all the vertices in my candidate solution are going to be within the subset or of the input itself.
right?
So you're
But
not
it
going to
can
get
be,
like,
but it can be repeated, right? There is no guarantee, like they cannot be
yeah,
repeated.
you can assume you can assume that it's correct. Like a click isn't going to give you repeated vertices either.
Oh, so we can assume it does not have repeated vertex
Yeah,
being
I'm not.
returned.
Yeah. So like, I'm not trying to blow up your verification step with tricky solutions. I'm just like, hey, this looks like a right solution to me. It's the right format. It's got the right rule set of like, you know, what a solution should look like. Verify it against the input to see if it's the right solution. That's all.
Right, right. So basically, we can assume it's probably a solution, probably from an algorithm that's flawed, whatever, but it's not going to give you completely nonsense answers like wrong data type.
Yeah.
Like a loop giving you a limited amount of vertices repeated or whatever. So it's at least at a glance, it may look to be worth considering, right? But we still need to verify everything. For example, if we have a ST pass problem, we still need to check S and T. We cannot just assume the return will have S and
The
T.
mindset you should go into this is that someone out there is trying to design a black box that solves this problem.
Okay.
And you are verifying that their black box is coming up with the right solutions. Therefore, you can trust the black box to be part of your reduction.
Okay.
And that black box is trying its best to answer the question, but you're unsure if the black box works or not. So you're going to go check it. And you can assume that that black box is trying its best to give you a solution, not like, oh man, I'm going to try to trick the verifier with these like wonky solution sets.
Okay. And then for the runtime justification in this portion, how tight do we need to be? So to give you an example, if you want to check if for each edge that there is, like for each vertex, the edge exists in E or whatever, there are several different ways to do that. And we may come up with N plus M or N square. Like,
Be as
do we have to
clear
detail
as be as clear as you can with your verification. Be as clear as you can with your transformation, and then give a runtime based on that. That right. So like if your runtime matches your intent but doesn't match what you wrote down, then that's a problem. You need to have your runtime match what you are writing down, and I think that's it. So like if you wanted, so like for example, right? If I wanted to, you can do. I don't suggest this because you'll make your TA sad or even angry. But I've always said, like, you know, if you wanted to do something like, you know, oh, I'm going to traverse through this graph, which is O of n plus m, but just to be absolutely sure that I have checked every single vertex and edge, I'm going to do it once for every vertex that there is. So it's O of n times O of n plus m, and therefore it's O of n squared plus O of plus nm. That in its entire like context is fine, in that I can give a really slow runtime. I gave the clear steps on why my runtime is really slow, and my runtime is still polynomial, and my runtime is correct. Like you can do stuff like that.
Yeah, but there is cases like you can argue it could be either n plus m or n squared. Like, can we just say n squared overall, especially if there are other steps already take n squared?
Nope. You should give the steps that would make it L of n squared. If it's left to interpretation, you have not given enough detail. You should make your steps very clear and have a runtime that matches it in a very clear way, such that there is no room for interpretation.
Okay, but if when we are combining at the end, say if one step is clearly n plus m, another step is n squared, we can still combine
you
into
can
n
say,
squared.
yeah, you can just say O of n squared is the step that dominates, just like any other runtime. Yep.
Okay,
yeah.
Thank you.
Students often confuse by we no longer care about things being optimal to we can give wrong runtimes. That is not the case. You can be as suboptimal as you want, as long as your runtime still matches the actual steps you are writing down, you will be okay. But it has to match. If it doesn't match, you will lose points for a wrong runtime. Could you imagine like a computer scientist is about to prove that P equals NP or P doesn't equal NP, and you read through their proof and their runtimes are all wrong? Is that okay? Like that's not going to be okay, right? That proof is like completely tossed out because there's information in there that's wrong. Even if it doesn't like have a material effect on the actual like this runtime is still polynomial, you still just can't give us like, oh, a wrong runtime and be okay with it. Jafar?
Hello.
Hi.
Thank you for this session, Joves. I have the same question. Okay. I read several places where if we are checking if a vertex, if the edge is existing for each vertex, for example, this is O of n plus m. Till now, okay, I can do it in O of n plus m with some data structure, but from what I understood from this course, it cannot be done in O of n plus m. I don't know how this O of n plus m came. So is there a way to understand it now, or it's feasible? I can say of n square because for each n I will go and check each m, so it will be of n m, and that's it. Okay, we can
Sure.
say something.
You can say assuming I use a adjacency matrix and I want to check that every two pairs are connected or not. Therefore, it's all of n squared. That's fine.
Okay,
You can do
great.
that.
So I will not lose.
Yep.
Great.
Do not
Second,
write optimal solutions that you do not understand.
yeah,
this-
this is what I'm
in this
asking.
context. Yeah.
Should I understand it now, or I can skip it for now? It's fine. I can make O
If
of
you
n
do
squared.
not understand an optimal solution, but you
Yeah.
understand how to solve it with a brute force polynomial approach,
Yeah.
do that instead. That is
Wonderful.
what I recommend.
Thank you very much. Another small question. You said that we cannot assume it's of size k. I don't understood the statement. Can you please give an example on this? Very
Yeah.
detailed
So if
example on
in
the
the
question.
click problem, right? In the click problem, you are looking for a click of size k. You can
Yeah.
assume that the click I am getting you to verify is of size k. I could be a few off, right? I could have, I might give you like, if you're looking for a click of size 100, and I'm like, oh, I found this click. This is the solution, but it's only of size 90. That doesn't solve your problem. You have to check to see that there is
Okay.
100.
Yeah. So we have to
Yeah.
do two checks. One, checking it is a click, and two, checking the size of the. Okay, this is intuitive. Thank you very much.
Yep. And that's not me trying to trick you, right? I don't know. I thought this was a size 100 click. My black box found this click, and it claims it's 100. Can you check it for me? You wouldn't just say like, oh, it's a click, therefore it's done. You would say, oh, does it actually meet the requirements of a size 100 click? Right.
Yeah. Thank you.
Yeah. Because finding a click of size 3, always a size 3, is not a hard problem. Finding a click of size k is a hard problem. So if you don't verify the size without the size aspect of it, it's actually not that hard of a problem.
Yeah, but if we say also, it occurred that maybe we are trying to find a click with size 2000. Is it a hard problem?
Nope.
It's not a
Finding
hard
a
problem because
click.
it's a constant.
Yep. Finding
Yeah.
Finding a click of exactly size 2000 is not hard.
Yes, but of size k, it will be hard because the input right now cannot be checked in polynomial time.
Right. So that's
Yeah.
why you actually have to verify it. Otherwise, you're just not like really verifying a hard problem.
Yeah. But
Okay.
but still finding a click in of size 2000 is polynomial time.
Yes.
Yeah. And finding a click of size k is NP. NP complete. Not NP complete, it's NP. I don't know if
It's
it's NP
NP
complete or not.
complete.
Yeah, this is complete. I don't know, but the NP, yeah, I'm sure
Right.
about it. Thank you.
By the way, all problems in the class P is also in the class NP.
Yes,
So
yes.
be careful there. Anything that is verifiable in polynomial time, and if you can solve a problem in polynomial time, I don't want to say with absolute certainty, but I think you can verify it in polynomial time. I think that's like some weird like class of problems where like verifying a problem could potentially be harder than solving the problem. But I think if you even then solving for all possible solutions is considered polynomial.
Yeah,
don't
I
worry too
think
much.
from the lectures it was a circle inside a circle, so we will never
Yeah,
find
yeah.
a P not in NP. But there's a question. David is asking, verifying a click of 2000 size is polynomial, but finding it is not polynomial. I think it's polynomial. Finding a click of
Finding it
size
is
2000
polynomial, and I'll leave
is
that
polynomial.
up to you guys to figure that out. All right. I'm gonna try to move on. Mujanatha?
Joves, yeah, thanks for taking question. I have two different questions. One is in the NP problems, we came across some of the graph concepts like induced subgraph, isomorphism, etc. I think we did not discover this in the past. Are there any list of graph properties, graph problems that we need to master for the exam 3?
I will go over stuff. Like, let's try to focus questions on the actual content on slides because I always have more slides that we'll get to it eventually. All right, James?
Yeah, I just had to give audio permissions. Can you hear me?
Yes.
Okay, so I have a question on why I still don't understand why we can't use K for the runtime for proving problems in NP. So for example, for the click problem, we're trying to prove that like an input is a click of size K. What if we first check that before we check that the input is a click, we just check that the proposed solution is of size K. So like I'm assuming the click can be provided as a adjacency list format, for example, as a graph. So you just need
It's
to
not
check
that you can't do it. It's not that you can't do it in O of K. It's that the O of K runtime is considered pseudo-polynomial because K is representative of a magnitude. It's not representing the input in any way. It's just representative of a magnitude. So while O of K intuitively is less than O of N, less than equal to O of N, and is within the bounds of like, being pretty optimal, right? Checking the size, you still can't use it just because K is a number. Polynomial runtimes is not always concerned with what is the fastest. It is the complexity class. And O of K being pseudo-polynomial, being a magnitude is not considered polynomial. That's it.
But I don't understand, like K is part of the input and so is like the nodes and the edges. So why are we treating like the nodes and edges as like regular like integers and then like K as some special pseudo
It's the same reason that it's the same reason that knapsack of O of N times big B is not considered polynomial because that big B is a number. Even if that big B is within some constraints, the representation of that number is not a polynomial relationship. So K here being just a number and not a a input of some things that you're looking at, it's just a number. Any runtime based on K will not be a polynomial relationship.
Okay. Yeah, I'll probably need to go back to understanding knapsack. But yeah, I guess for now I'll just use big O of N just to be safe.
Yeah.
Mhm.
Yeah. And there is a case to be made that you don't always have to fully understand something to do the pragmatic approach. And the pragmatic approach here is that if any number, if any variable represents purely a number and doesn't represent like a set like a array of things to inspect, if it's just a pure number, don't tie your runtime to it because it'll be pseudo polynomial.
Got
Like
it.
you
Thanks,
can,
James.
even if you don't understand why, right? When you go and do your solutions, you can just follow the pragmatic thing that you can get away from it. Yeah. I mean, sure, it's always best to understand why, obviously, but if you haven't gotten there by the time the exam comes out, just go with it. Trust in that what I've told you is true. Yeah. All right, Michelle. That's the last question, and then I have to move on. I have like a bunch more
Hey,
slides.
Joves,
I haven't gone through practice problems. Yep.
Yeah, no, I totally understand. My question was kind of similar to the last person, so I should put this in the chat, but I think I get what you're saying. So verifying the size of any solution is always going to be O of n, right?
Right. Yeah. Because the solution I gave you is not going to be junk, and therefore the solution I give you at most can have all of the vertices or all of the literals or all of the variables or all of whatever comes into the input, and therefore you can just say, okay, well, it takes O of n to verify if all the vertices, if there's k vertices, because all the solution can at most have n vertices, right?
Right. Okay. Got it. And so in the
Yep.
input transformation, or I guess when we pass n into the inner function, we should probably use n as a value for one of its variables.
We'll get there. So
Yeah, of course.
okay. All right. Moving on. All right. So now the second part is that you need to demonstrate B is at least as hard as the chosen A. Okay. I already went over why this reduction works. So how do we do that reduction? Well, we have to show how an instance of A can be converted to an instance of B in polynomial time. Okay, so that's the input transformation. And then all instances of A must be converted to instance of B. You do not get to choose what those instances of A are. As long as the input is valid to A, it must have a correct or a conversion to the instance of B, right? There are some special things you can do, but for the most part, it doesn't happen. One thing to consider is that when you do from like a sat to 3-sat, a lot of times those kind of transformations can say, okay, we're going to ignore any one literal clauses because those are immediately satisfied. And so it kind of can simplify the transformation. But that does not mean you filter out any problems that have single literal clauses. That means that if you have a single literal clause, you do some kind of like, additional work up front. And therefore, I only concern myself with clauses of 2 or more literals. That's okay. You can't say, oh, we just ignore all clauses with one literal, or we only accept CNFs with clauses of 2 or more literals. You can't do that. You can't avoid some kind of input. You can just say, oh, for some inputs, we are going to already solve or take care of in a separate way, and therefore we're going to work through this. Okay. You do not get to choose the input for A. You want to force a solution to B if there's a solution to A. So anytime A has a solution, B must also have a solution that can then be transferred to that A solution. You also must give a runtime and same spiel. If you have a target, budget, or goal, you can't use it as your runtime unless you bind it. You can be as slow as you want as long as it's polynomial. So very similar, right? And never solve A to create an instance of B. So anything like, oh, I first find the click in my input and then I do this is not okay. Or first I find a satisfying assignment to this sat before I transform it to this other sat. You can never do that because if your transformation requires you to solve any part of A, that transformation in itself cannot be polynomial or cannot be known to be polynomial because solving an instance of A is already not known to be polynomial. So by having to solve something of A in order to get to an instance of B, you've broken the rule that your transformations must be polynomial time. And then you have to do it in the other direction. So you have to show how a solution to B can be converted to a solution of A in polynomial time. Okay, all solutions of B must convert to a solution of A, matching the input that created that solution. If B has no solution, then A also has no solution. And you have to state this actually. Every time you miss this statement, you lose points. It is one of the easiest penalties to apply. You have to make this statement because everything from every output of B has to be mapped to an output of A. And if you skip the no solution part, you have missed one of the mappings. Also must be big O. Don't give it in K, B, or G. And then again, can be as low as you want, as long as it's polynomial. Okay. Any questions about this part? Eduardo? All right, your hand went down, so I assume you decided to do that. Mahmoud?
Sorry, can I still ask the question?
Yeah, go ahead.
I was on mute. So let's imagine, this is for reduction. Let's imagine we're reducing a problem, NPC known to black box. Is it unrecommended for us to modify the graph that we're going to pass through the black box? So let's say, we have a graph or as an input for the click that we need to modify somehow to force a solution to the black box. And let's say, in order to force the solution to B, we might want or try to be creative and do something with the original graph or G modified. Is it recommended for us to not touch the graph and just add, I think on the book they call it, what do you call it? I'm forgetting the name, but yeah. So should we can we modify graph?
Yeah, you can and you should. That's the exact point of this. You're trying to transform the input to from A such that if there's a solution to A, there's also a solution to B. And the solution, the B might, the input to A might not meet the requirements for a solution to B. You need to force that. Now, it's very, you have to be very, very, very careful, okay? This is the key right here. If there's a solution to A. You cannot add something to the input going from A to B such that you force a solution to B no matter what. That is not the point. B should only be able to find a solution if there was a solution to A originally. And that's how you convert it back. If you let's say A is looking for a click, right? And B is looking for a click plus something. You should not say, oh, let me create a click plus something for my input to B so that B absolutely will have that solution. That's not how it works. You should only force a solution to B if there's also a solution to A.
Got it. And what I was talking about are gadgets. I think that's what they call it if you end up. Yeah. So.
Yeah.
Okay.
Yeah.
Thanks.
All right. Yep. Mahmoud?
Yeah, so kind of building on this a little bit. I understand that if we're adding something like a part to a graph or something or rather, that makes sense. But for example, the white gold problem, there's a T and a C, for example. If your original input, like for example, the A box doesn't have a T or a C, are you allowed to create those, like the colors in the graph? Are we allowed to say, oh, just make all the points in the graph this color or such a certain number of
You can
points
do anything your mind can imagine to the input as long as you don't lose the specifics that make it so that when the output comes back out, you're able to map it as a solution to the problem A. So as long as you can go from a input to A to an input to B, such that the B solution can be directly mapped to the solution to the original input, you're fine. You can do anything your mind can imagine.
Okay, and then the second question I had was, you said if B has no solution, then A also has no solution. Is this also similar to the point in the guidance document where it's like, if B has a solution, then A has a solution, and if A has a solution, B has a solution, or is this something completely?
Yep. Same.
Okay, so it's one of those four things that they listed in the guidance document.
I'll go over that as well. Yep.
Okay, sorry. Thank you.
Yep, no problem. All right, last question, Bing.
Hey, just a quick question. Can we always use capital S and capital H? These standard letters, we can just assume like the solution from the output transformation, etc. Or do we have to clearly say H? Let H represents the solution returned by the black box.
You should tell us what your letters mean. There's no
Okay.
standard to this. I mean, there is some letters that I will always use, but I always state what that letter stands for.
The reason I'm asking is because the model solution just says otherwise return H as the solution without saying what H is. That's why it's like.
I will take a look as I go over them. But
Okay.
If there is a mistake, I will ask the right people to correct it.
Okay, but can we modify them? We can modify them, right? It's not like the previous
You can
pass,
absolutely modify. Yeah, you should
so we
modify
don't have
the
to
input.
make a copy to modify.
Oh, no. You don't have to make a copy. You can modify them directly. That's fine.
Okay. Okay, thank you.
All right. So the third part and the final part is that you need to show that B has a solution if and only if A has a solution. So the if and only if is really important. This implies that if B doesn't have a solution, A also doesn't have a solution. There's multiple ways to do this, and I'll suggest some to you. So the A is if A has a, so if your statement is if A has a solution, then B has a solution. That is, one thing you're trying to prove. The other direction is if B has a solution, then A has a solution. Okay. This is the standard both positive implication. This is a positive implication, and this is a positive implication. You can also say if A has a solution, then B has a solution. And if A has no solution, then B has no solution. So what we're going to do is we're going to take the second one and we're going to turn it into its contrapositive. Okay. Contrapositives are always equal to the original statement. Okay. If B has no solution, then A has no solution. And if B has a solution, then A has a solution. So this swaps the first positive with the contrapositive. So this is now the one that we're going to change into a contrapositive. Because again, contrapositives are equal to the original statement. Okay. So if A, then B, then if not B, then not A is the contrapositive. Okay. D is if B has no solution, then A has no solution. And if A has no solution, then B has no solution. What this is going to do is swap both positive implications with their contrapositives. Okay. Now, I would avoid doing this. It is very difficult to read. It's legal. It's hard for you to write. It's hard for your TAs to read. So some combination of you making a mistake or the TA misreading it is likely to happen, and then you're going to have to do a regrade. So I don't like it. Only do this if you're kind of a mad person and you just want to mess with it. Okay. So you can pick any one of these, A, B, C, or D. We will that you feel most comfortable with. We will accept it. Okay. Both directions are required. What you don't want to do is accidentally argue the same direction twice, which is using the statement itself and then its own contrapositive, right? Because this statement is true. This statement is also true. Always, 100%. The contrapositive of a statement is always true. You're just arguing the same thing twice. The only way you can argue the if and only if is if you argue both statements. Okay? Don't do that. I mean, do that. Don't do the using the same statement twice. Now, I myself like this one. I think this one's okay too. I'm kind of meh about this one. I don't like this one too much because I like to keep my initial statement true. If A has a solution, then B has a solution, because that is exactly the positive statement I'm trying to prove. And then I'll use one of these depending on which one I feel is easier to argue. This one I would really, really, say try to avoid. This only really happens if a statement, if the student accidentally uses this and it happens to work. But I tell students not to do this. Now, you can pick any one of these that you feel most comfortable with and just memorize that one and say, I'm only going to do this one no matter what the problem is. And that will be fine. That will work for you. If you're a little bit more comfortable with it, you can say, well, I am going to always make this statement, and then I will choose which second statement I use depending on how the problem is presented and how I'm arguing with it. If you're a little bit more comfortable with this, that's what you can do. You can also use this if you really want. I will avoid this. You can even use this if you really want to test how lucky you are versus how good a TA is grading it. if you want, but I don't recommend it. And yeah, Nanfen? You're muted if you're talking.
Oh, sorry, I didn't know that. So, I
Yeah.
want to know that confirm for number C here. Normally, I saw the same pattern when we just reduce from the known NP complete to the unknown. So here, I think C is normally the way. B is representing the unknown black box one, and A is the known NPC problem. So this is something we have to do. And the one thing is I want to know the runtime. I was always lost when I tried to come up with a long runtime during the when we just proved the NP problem, NP complete problem. Do you have any tips on this? I know we have a long like a list of the NP known NPC for reference to go to proof and then the unknown one. And I think in the lecture notes we didn't cover all of them. So are we going to learn that by ourselves, or you're going to give us some like instruction on this as well, such as Raj or Tab? Uh-huh.
All the so the way I like to look at these are kind of like your toolboxes. So you have your lecture black boxes that are your primary set of tools. These are your hammers and screwdrivers and wrenches. These are tools that you will, if you have all these tools, you will be ready to solve any of the problems we give you. And be really, really good with these basic tools that are the black boxes cover, well, the NP complete problems covered in the lectures. There is a second set of tools that are coming from the book. Some of them are really advanced. And if you have knowledge and access to those tools and you're good with them, then yes, they could help in certain reductions. But I would say that you should certainly the list of allowed black boxes is a hard, set. You cannot go beyond that set of black boxes and try to pick additional NP complete problems that's sort of beyond the scope of this class, or even like problems in the book. You can't reuse them. We have found in the past that when we allowed students to do whatever they wanted, one, it was really hard to grade, and two, they oftentimes shot themselves in the foot because they shouldn't have used a gun on a nail. So that's I know that sounds silly, but students, when given full freedom, tends to hurt themselves more often than when you don't give them that much freedom. So we have set a list of black boxes that you're allowed to use. I would be familiar with all those black boxes going into the exam. Okay.
Thank you.
But again, just like exam 1 and exam 2, your practice problem, your homework problems are the best, the things you should focus on. The practice problems with model solutions is your next set of problems that you should really try to understand. And then there's going to be a set of recommended problems that you should try your best to do them. But if you only have limited time, I would say the homework problem, the assigned homework problems, and the practice homework problems. Hung?
And talking
Oh,
about
yep.
the runtime, I think I just have too many questions. Just runtime. Do you have the tips to come up with a runtime for different NPC problem, such as we have like a graph related one, and we have those like Boolean related one, and also we have
Yep.
some like the linear programming related NPC problem. So do you have any
Right.
tips to?
Yeah.
Uh-huh.
Write the transformation or verification steps that you can be sure the runtimes are. You don't have to be really, smart or really clever about the transformations or the verification steps, right? So don't try to find optimal runtime. Just be like, okay, well, I think it's either O of n or O of n plus n or O of n squared. I'm not quite sure which one it is. I will write the steps to force it to be O of n squared. That way, O of n plus m is technically more optimal, but I know I can turn this into an O of n squared approach if I give the right steps to force it to be slower. And then you have an O of n squared runtime. That's correct. You don't need to try to, if you're unsure what the runtime is, force it into the runtime that you want to write down. That's all.
Oh, okay. So it's saying we're not required to have the optimum runtime. As long as our transformation makes sense, then the solution should be correct.
Yep.
Is that right?
Yep.
Okay.
Yep.
Thank you.
Yep. All right, Hung.
Hi, can you hear me?
Yep.
Yep. So for the exam grading, I noticed that we don't explicitly state something that we don't get the points for it. For choice A here, it doesn't explicitly say that if there is no solution, then B doesn't have a solution or something like that. So if we try
That's
to
because
use
that's because the contrapositive is always the same statement. It's just said in a different way. So the contrapositive so if B has a solution, then A has a solution, is the same as saying if A has no solution, then B has no solution.
Okay, so what if we write in another N and say if there's no solution, then no solution? Will we get points taken off or?
Wait, sorry, if you say another what?
So let's say we pick A as our answer, and then we do
Yeah.
another N at the end, saying and if B or A doesn't have a solution, then A or B doesn't have a solution.
You can always write more than you need to, and if there's no contradictions, you won't lose points. The problem with writing more and more and more is that you run the risk of writing a contradiction to your own statement or writing the wrong statement, right? But
Yep.
the negative of not writing enough is that you miss something. So you have to find a balance that you think works best.
Yep, that makes sense. Thanks.
Yep. All right. Bing?
Hey, Joves, is the point allocation for NP completeness proof similar to previous written questions, or they're different because they're now 4 parts?
Sorry, say that again?
I mean, the point allocation, are they similar to the previous big free response questions, like 20 points in total?
There's 20 points in total, and how they're broken down can depend on the problem. So I would just take a look at the homework regrade threads when the homework grades are released. But I will probably go over them a little bit more during the exam prep.
Okay, but it's not like the previously like runtime is like 4 points, 12 for the algorithm or whatever. This is more, maybe more evenly
Yeah,
for 4 parts.
it's broken differently. So
okay.
well, yeah.
Thank you.
All right. All right. So things to watch out for. So these are the mistakes that we see. So going from unknown to known is really bad. Don't do that. Describing how the unknown works. We don't know how the black box works, and we don't care. The point isn't to find a solution to the black box or even find a solution to the known problem. We're just looking for a reduction to prove complexity, right? We're not trying to solve any of these problems. Solving from some part of A before using B is really bad. So like if A is the click problem, then we attach something to the click. You cannot assume there's a click, and even if there was, it would take a long time for you to find it. So don't do that. Finding the click to attach to would already be non-polynomial. Okay, assuming the input to A has a solution is a bad idea. Since the input to our problem has a click, you can't assume that, right? You don't know if the input has a click. This constrains the input to A, which is not allowed. Not transforming the solution to B as a solution to A is allowed. Even if the solution is exactly the same, you have to state it. You have to say, return the solution to B as the solution to A. You have to make an explicit declaration of what you are returning. Now, I said before that A has no solution, you have to return as a solution to B. If your solution is exactly the solution from B to A, you can skip that part because your statement is going to be take whatever you get from B, return it to A. That includes if B returns no solution, that would be returned to A, right? So, but you have to explicitly state that you return that solution in some way. Okay. Not stating that if B has no solution, there is no solution to A. So this is like, I think one would say -1. So always do this. Not giving runtimes as big O, saying it is polynomial is not enough, and it needs to be stated even if there's no transformation. So even if you say, I take my solution to B, I return it as my solution to A, you then have to say, this is all one. You absolutely have to state the runtime because those are the pieces to the proof that's required. You cannot skip that even if it's obvious, okay? All right, so here are going to be strategies of what you should do on each problem type. I'm going to go over it a little bit quickly because I think it's more relevant when we come to the exam prep. So I'm not going to answer any questions on it because I think we will have more time to prepare for it later. Okay. So 3-sat to exact 4-sat is an example. I don't know if you've seen exact 4-sat yet. Maybe you have. We'll take a look. Sat to stingy sat is an example. So you're just basically taking from one sat-like problem and going to another sat-like problem. Okay. The proof is generally very simple. You just make sure that you verify the assignment, sat assignment. So take the assignments, verify every clause is satisfied with those assignments. Make sure to count anything. So if there's some target or some goal or some budget, make sure you count it and that it's met. Okay. Make sure to verify any special conditions in the solution, right? You don't have to verify that the input is valid. You don't have to verify that the solution is of the right type. But if there's any special conditions like, oh, only certain number of clauses can be satisfied or only certain number of literals can be set to true and so forth, you have to verify those special conditions. On the input transformation, you need to maintain the CNF form, okay? Unless otherwise told, any sat problem we give you will take in the CNF form. It is still a sat problem, just with additional requirements and limitations. And one of the requirements for a sat problem is that it takes in CNF. Now, remember how I told you, you don't have to verify the input is correct. You don't have to verify that for your solution. However, when you make a transformation, your input needs to be still the correct input. You could mess up the input transformation, and therefore the input is no longer correct, and that's a penalty against you. You know, our input will be valid, but your input transformation could mess that all up. Don't do that. Be careful. Be sure to maintain the equivalent logic. If you mess up the logic in your transformation, then you are not going to be able to remap the output to your correct to your answer to problem A, right? So you need to make sure that the logic is maintained in some way. Be sure to only add literals and clauses. Okay, that's the only thing that you're really adding, unless you're adding like additional variables or whatnot. But for your CNF itself, only add literals and clauses, right? You can't add a true clause. You can't add a false clause. You can't say, oh, you know, the CNF or true, the CNF or false. You cannot, you know, and false and true, what have you. You cannot add a true or false statement to your clauses. On the output transformation part, remember to remove any added literals or variables, right? So if my incoming input is A, B, and C, and my solution is A, B, C, and D, this solution is no longer a valid solution to this input, right? So any added literals or variables needs to be cleaned up. You don't need to clean up the clauses because the clauses is not part of the output. A SAT solution or a SAT algorithm does not return back the clauses that came in, so you don't need to clean that up. On the correctness, there's two ways to do this. You can either establish the equivalency of the two SAT problems after transformation. So you can say logically they're the exact same problem, and therefore a solution to B maps directly to a solution to A. Therefore, if A has a solution, B has a solution. If A doesn't have a solution, B cannot map a solution, right? So you can make that argument. Then argue the if and only if. Or you can argue them one at a time. If A has a solution, I've done the transformation needed to get a solution to B. If A doesn't have a solution, my transformation cannot possibly create a solution to B, and therefore A has no solution, B has no solution. You can argue them separately, or you can argue an equivalency and then make the if and only if argument. Okay, either is fine, up to you. The second set of problems we have is graph reductions, which is about connectivity, and here are the strategies, right? So these look like the IS to click plus IS, or the click to the subgraph isomorphism problem. So the NP proof is make sure that you verify the graph carefully, okay? If the graph contains a click but isn't separated, you must separate it first. What does this mean? If I say, given a arbitrary solution, make sure it has a click. My statement implies I am going to take an arbitrary set of vertices and edges, and I am going to look for a click, right? Now, I told you I'm not going to give you a junk answer or a attempt at a junk program. But if I had a black box that was a path through, you imagine like when you're doing coding, one of the first things you do is a really dumb method that does a path through. It takes in the input, it spits it back out as the output. That's your initial black box. If that initial black box comes out and you do your verification and say, oh, look to see if there's a click in this this proposed solution, it's going to take a long time. The reason it's going to take a long time is because it's going to just find a click in the arbitrary graph. You can't do that. What you can do is isolate all the vertices that could potentially be a click and then verify it's a click. Okay. Finding a click in the arbitrary graph is not polynomial, right? That's what I was getting at. Make sure to count anything or check the sizes for the solution. So if I need a click of size 20, make sure it's size 20. If I need a click of size k, make sure it's size k. Try to avoid degree counting, which is usually wrong or is much harder. So a lot of students will say, well, if I'm looking for this particular graph, I'm looking for, 5 vertices that has 7 degrees. I am looking for 10 vertices that's like 8 degrees. Those almost never work. There's almost always ways to draw graphs that fit those degree counts that don't work the way you think it will. We have very talented TAs that love busting student solutions, and they will draw the most, amazing graphs that will break your degree counting. Now, you can count degrees to isolate vertices that you think will make up your solution. So, like if I'm looking for a click of size k, I can isolate all the vertices that have k minus 1 degrees, and then check those vertices to see if they form a click. That's polynomial because I've isolated the vertices that could potentially form a click, and then checking to see if those vertices form a click is n squared. And so that's fine. You just can't go looking for a click in the dark. You can isolate it and then do it. What happens if I don't have the right number of vertices that's k minus 1 degrees? Well, it immediately invalidates my solution. I'm not trying to solve the problem. I'm trying to see if I have a correct solution. So those kind of things you have to be aware of why that works. All right. So for the input transformation, do not try to find what you're looking for before modifying. Finding a click to edit is not polynomial. Force your unknown problem to find the solution for you. Remember your B, K, or G. Your click might have a K input, and that K input might be the same K going into your black box or going into your unknown problem. But you have to set it. You have to say K equals the original K. You have to state, otherwise it's dropped and you're in trouble, okay? Be mindful of accidentally adding extra candidate vertices or edges. If you've done the quiz, you should hopefully have seen a solution that that could potentially cause this mistake. Okay, you don't want to accidentally add vertices that can be used for a solution if there is no solution. So be careful. The output is isolate the thing you're looking for from the unknown output. So if you have a output, if your problem A is click and your unknown output is click plus something, you need to be able to find a click to return, right? You can't return the whole thing wholesale. Often just removing the added vertices or edges is not enough. This is something you need to be careful of. Because what can potentially happen is that you start with a click, and you're looking for, I don't know, what was the practice problem that you guys got? Let's see. Was kite one of your problems?
Yes.
Hey, Joves.
Great. Hold up. Let me get my train of thought. Okay, if kite is one of your problems, we can talk about that a little bit. Wait, which problem was on homework 10? Cool, kite. All right, so what this means right here, what this part right here means is that if you're looking for a kite and you take your click and you say, okay, well, add all the things I need to create a kite and then turn it into a kite solution. And then the kite solution comes out and goes, okay, well, just remove all the vertices that I've added and I'll have the click. If the original input somehow had a kite already, your kite problem is not going to know your kite black box isn't going to know which vertices was added and which vertices was not. It could potentially find a kite that was in the original input. And if that happens, removing all your added vertices does not actually remove the tail to the kite. You could potentially just have the kite, the entire kite as a sorry, post transformation output, and that would be bad. Don't do that. Okay. And then your correctness, you argue why the solution for the unknown can only be found in G prime, which is your transformed graph, if the original G has a solution to your known, and that is the approach you should take. All right. I have some questions, so I'll try to answer. Mahmoud?
Yeah, so maybe I'm not visualizing it, but how do you isolate like a click? Like there is a click black box, so could we just not say run the click black box to find the click? Is that something that we
No.
could do,
Okay.
or
Let's see. All right. So if you had a click, right? And I'm just looking for a solution to a click, right? If I had a whole bunch of other vertices in here.
Hey, Joves.
Yeah.
Hey, do you think you could do like the picture I mentioned in the chat? This was like the homework that we had last week. I was actually really interested in knowing like how would we go about that, because I think for the kite it was pretty simple because we're just adding a basically a chain of vertices, but here it's a bit different. Where
Like
it's
go
not
over the solution or go over, what do you mean?
yeah, just like how would you deal with that, right? Because a chain of vertices is like much easier to kind of find and isolate versus like a structure like a star.
For finding the click?
Uh-huh. Yeah. Here I posted the image as well.
Yep, yep. Okay. Second.
Thanks.
Okay. So if I was to find an arbitrary click, right? And I'm saying I need to find a size 4 click or a K size click, right? Finding K size click is really hard because I would have to check, one potential brute force would be, okay, I am going to check for all vertices of where degrees is greater than or equal to n minus 1, right? Because that's how you, right? K, that should be K. My bad. Right? Right? So this is saying, okay, find all of the vertices that could potentially be part of a click, because I need to know that the degree is even allowed. If I have anything that's less than K minus 1, then it is not attached to enough other vertices to be part of a click, right? So first we isolate all the vertices that has this feature in it. Now, there can be a lot of vertices that have this, right? I could potentially have all n vertices or up to n vertices that have all this, right? And now I'm doing some sort of combinatoric stuff like, okay, well, choose k out of n, check if they're click, no, choose another k vertices, check if they're click, no, do another k vertices, right? So you're basically doing a combinatorics factorials brute force check to it, right? And so looking for a click in an isolated graph, really, really hard. But if all I need to know is if my solution is correct, and my solution is only a click, right? Then all I do is check if the input, if my solution set is a click, right? Doesn't really matter how many there is, doesn't really matter how many degrees are. I just need to know if my entire solution proposal is a click, right? But that changes if I'm given a kite or a flower. I think this is the flower problem. Okay, so given the flower problem, I can't say check if there's a click in here. The simple statement of saying check if there's a click in here means that this could be potentially a lot, right? What if, like I said, your black box is a pass-through? All I did was get an entire entire graph back, and now if I go, okay, well, look for a click, it's going to take forever. What I can say though is I can do this same process, and it's okay. I can say, find me all the vertices that have k minus 1 degrees. So that's 3 degrees, right? So that is let's do, okay, that's this one, this one, this one. This one has 4. Okay, so I found these, right? Now I need to find, I go the extra step, like, okay, well, are all of these connected to each other? And are they connected to a single vertex of k degrees? So that completes my click. I've isolated the click. If for whatever reason I do this on a complete graph, and I find that I have some number of vertices that are k degrees, k minus 1 degrees, and they're not attached to each other, I'm immediately done, right? I fail fast. I fail because I'm only allowed 1 click in my solution. And if I find a bunch of candidate vertices that for whatever reason are, k minus 1 degrees and they're not connected to each other, I don't have to go looking for the click. I've decided that there's no click, or there's not, either there's no click I'm looking for, or there's multiple clicks in here, which also isn't okay for a flower. Therefore, I'm done. So the idea is that there can only be 1 click in here. Isolate all the vertices that potentially could be in that click, verify that they're a click, and if it's done, then you have 1 click that you need for your solution. If you don't have it, then you don't have the click. If you have more than 1, or some of the vertices, like let's say I interject another thing in here, right? And I find all of these vertices, right? The second I find out that 2 of them are not connected to each other, right? Well, this shouldn't have existed to begin with. And if this doesn't exist, this exists while I'm trying to find this click, I'm also done. I don't need to be able to verify that or be able to find the click. That's not what my job is on the verification or even the transformation part of it, right? The transformation part of it, you can assume is the correct solution. And now I just need to find that 1 click. Does that make sense?
So just making sure I understand. We isolate all the points that have degrees greater than or equal to k minus 1, and then we check.
Or
that,
in this case, exactly k minus 1. When you're looking for a click in an arbitrary graph, you need greater than equal to k minus 1. But when you're actually verifying, I just need degrees to be exactly k minus 1. And I need k minus 1 of this type of degree plus an additional k degree vertex so that they all connect together. Because I know that this is going to be k, because this one has to have 1 more degree to attach to the stem. But all the rest is going to be k minus 1 and then 1 k degree. And then I make sure that this creates a flower.
So we find all the points that have k minus 1 degrees plus an additional one so that it's connected to the star. And then we check if those k points, the k minus 1 plus the additional one, are all interlinked. If they're not, you fail fast. And if they are, continue with the rest of the algorithm effectively.
Yep. Which is why verifying a solution can be done in P while finding that solution using basically the same approach is not in P.
But this is all on the premise that given a graph, we can verify that one exists using this method to some extent.
Yep. Yep.
Okay. So then my next question is, this is if this is a flower, but what if, for example, the click is embedded into another graph, right? We're trying to find the subgraph that's a click. Whereas, like, for example, the other points are connected to some extent. It's
So
not just
again,
the one.
There's a lot of practice problems. I'll probably get to one eventually.
Okay.
And we'll see. We'll see how that works. Yeah.
Cool.
This
okay,
is just
sorry.
like trying to yeah.
Right. Thank you.
Okay, no problem. You guys keep wanting to get ahead of yourselves. It's fine. I appreciate the enthusiasm, but I'll get there. I'll get there.
We're so excited, Joves. We're so excited.
I know. It's fine. It's fine. All right. Last question, and then I have to move on. Shinkai?
Yeah, I think you probably addressed this. So just to confirm what I posted in the chat, that you mentioned it's hard to find a cliff from a flower. So the first step is to find the vertices of a star and then exclude those vertices and check if the remaining vertices are fully connected.
Okay.
So is it the solution to find a click from a flower? Or to verify there's a
So like if you're doing the verification, you want to be able to isolate the click, then to verify the click and verify the rest of the flower. If you're looking for an output transformation, there's a flower, right? Because your output transformation works. There's a flower, and therefore you isolate the click, return it. Doesn't really matter what the rest of the pieces are.
Cool. Thanks.
Yep. All right. Right. So there's another set of graph reductions. This is called these are pathing graphs. So this one's connectivity, which is your independent set, your vertex cover, your click. The other type of graph reduction is pathing, right? So you are looking for, say, rerouted cycle to traveling salesman problem with the budget, rerouted path to spinning tree, or a rerouted path to rerouted cycles, what have you. If you don't recognize this word, it's the same as a Hamiltonian cycle and a Hamiltonian path. So NP proof, make sure to verify the path carefully. Make sure all vertices are accounted for. So this is the one time where you actually have to verify. Well, not one time, but you have to verify the vertices accounted for, because if I give you a path, right, the rerouted path is a path through all vertices, right? So you actually have to check to see if all vertices are included in the path, because I could just give you a partial path thinking that this is the best solution, this is a solution, and if it doesn't include all the vertices, it's not a rerouted path. Same thing with the cycle. You have to verify all the vertices are accounted for. Okay? Make sure the path is a path, that the cycle is a cycle, or the spinning tree is a tree. So I could potentially give you a path that's not a path, that has a cycle in it. I could potentially try to give you a cycle that isn't a full cycle. So you have to be careful, make sure that these are actual things that I claim them to be in my solution. Make sure to count anything or check the size of the solutions. Use your graph black boxes. So you can use BFS, DFS, controls, prims, whatever. You have access to these previous black boxes for verification. Perfectly allowed. Okay. Input, consider what each rerouted problem is looking for and try them all if you have to. One such approach I take is like, oh, will this work if I'm using a rerouted path? Will this work if I'm using a rerouted cycle? I kind of do this for the other graph problems too. Like, will this work if I use a click? Will this work if I use an independent set? You may not, be really quick to be like, oh, what exactly is the graph black box or graph known problem you want to use? But you should be able to recognize, oh, this is a pathing graph problem, or this is a connectivity graph problem, and then kind of get to a set of problems or a set of known problems that you want to start with. Okay. Consider forcing path to be a cycle. What can you do to make a path into a cycle? Like if you're looking for a path versus a cycle. Considering leaves to be S and T. We'll see some problems that take on this form later. I think it's one of the practice problems. Forcing leaves to be S and T. Okay. And then, do you need an S and T? Is that something you actually require for your input transformation? Then the output transformation is generally pretty simple, but make sure to transfer to a path or cycle if you have to, right? So if you found a cycle and you need to turn it into a path, or if you have a path, you need to turn it into a cycle, be careful. If there's no transformation, state it and give it in an all-of-one runtime. So oftentimes any problem that doesn't require any additional transformation, say it and then give it a runtime, okay? The correctness, argue why the unknown problem can be reduced to finding a path or a cycle with all vertices. And then there you go. So the next set is set reductions. So this is your vertex cover to hitting set. I think that's one of your practice problems. The proof is generally pretty easy. Just make sure to verify each set and its contents or intersects. Make sure to count anything or check the size of the sets. Again, checking for size is super important, okay? So be careful there. Consider runtimes and how large the largest set can be. So one of the things that can be confusing is like, okay, well, I'm given n sets of items. How do I turn that into a runtime? Well, you can count how many, you can decide what is your largest possible set, right? Which is all of your known items, all of your allowed items. Kind of like a set, right? Your set clause has a size limit, right? They're given n variables and m clauses. How big is each clause? Well, each clause can only hold every single variable once, right? And therefore, your size of your clause is size n. And therefore, to verify a CNF is runtime all of n times m. Similarly here, you can argue that your largest set of possible intercepts or what have you has to be at most the size of all your items. Input only use allowed NPC problems for reduction. This is one I have to point out here because there's several set problems that's in the book that will be mentioned. And if they're not in the list of allowed known problems, you cannot use it for a reduction. So be careful. You can also go from graph or set, but be careful with set because literals are related in the set, whereas in a set they're not related, right? So like there is a relationship between A and not A that is implied through implications, but A and B on a set is not related. They don't matter to each other, right? So be careful there. Excuse me. It's usually a generation problem, generalization problem. I'll go over some of that in the practice problem. That is, you create an equivalent problem to be solved based on the generalization. So the you can say this by doing some transformation to this problem, it is equivalent to the problem I am trying to prove, and therefore, if A is exactly B through these transformations, therefore A is NP complete, B is NP complete. So you still have to go through all the steps, but that's sort of like the approach you would want to take. Consider the runtimes and how large the largest set can be. So usually size of allowed items is going to be part of your runtime, similar to how SAT uses N and M as its runtime. On the output, be sure to convert back to the thing you were looking for. And on the correctness, argue why the problems are equivalent, and then argue if and only if. So this is very similar to like a set. I can say, okay, well, problem A and problem B are equivalent. Therefore, if A has a solution, B has a solution. If A has no solution, B has no solution. Or you can argue them one at a time. That's also okay. By doing this transformation from A to B, if A has a solution, B has a solution. And by doing the transformation from so forth and so forth, therefore, if A has no solution, B has no solution. You can do it kind of like however you feel, but I think with set reductions and SAT reductions specifically, the equivalency comes up pretty often. Eduardo?
Yeah, quick question about the graphs. You mentioned that in the output, often it's not enough to just say, oh, let's just remove the added vertices or whatever we added and yeah, we should match the solution to the reduction or the A problem. Why would that not be enough?
Okay. So suppose my original input to my click problem, because remember, you cannot filter out any inputs. So I am looking for a flower. Right? Okay. I am going to force a solution to my problem if there is a solution to be. So I am going to, the correct solution to this, and hopefully Dr. Vertical Sort, is actually to add a star to every single vertex. There are other solutions to this. Don't freak out. I'm not going to bother answering if your solution is correct or not. Just going to tell you what a possible solution looks like. And then I'm just going to do that on these because it's quick. Okay. Now, I know all the red vertices are added. I have access to all the vertices I added. That's great. My height, my flower black box could potentially say, okay, well, here's my flower, and I am going to remove all the vertices I added, which leaves me with the click. Great. But your black box also doesn't really know which vertices you added and which vertices you didn't add. So if the original input for the click problem also happens to contain a star attached to the click, it could potentially find this, right? Now, what happens when you say remove all the vertices I added? Well, you didn't add these vertices. These vertices came from the original input. So when I return all the vertices you didn't add, I'm going to include the star into the click, and that is wrong. That is not a proper click to the click problem. And therefore, you cannot just say remove all the added vertices. You have to do something more than that.
Right. So we should basically say keep the click and remove the stem or the star vertices.
Exactly.
Right? Okay.
Yep.
Got it. Got it now. Thanks.
Yep. Okay. No problem. All right. So there's also summation reductions. I know everybody wants to get a break. I'm going to try to finish these slides, take a break, and come back to do some problems. So bear with me for about 5 more minutes. Summation reductions. So subset sum to knapsack is a classic one. Your NP proof is generally really straightforward to verify. You're just verifying all the rules are met, right? So does a solution set add up to what we are looking for? Does the weight limit get the budget limit requirement is done correctly? Is the target over it? Is that correct? So right, you really only verify things that are really super obvious. So I think the NP proof part is actually super simple. Okay, so you don't really have to remember this. This is just sort of an argument to help you out. So students will say, well, isn't adding a bunch of numbers arbitrarily like not arbitrarily, isn't that kind of pseudo polynomial because you're adding to some x, which is a target? And so as I'm adding to that target x could potentially make my NP proof pseudo polynomial. But remember, adding to x, right, takes the adding of log x bits n times, right? Because x is my maximum sum, so all other numbers are smaller than that. And if all other numbers are smaller than that, when I'm doing addition, I'm doing it n times. I'm adding possibly n numbers to reach that sum. And because it's n log x, because log x is what represents x, and I said the log of any number or variable makes it polynomial, n log x is a polynomial runtime to add up to x. Okay. You don't have to super remember this. You don't have to be like, oh, what does this mean? Just know that if you say, okay, well, when I'm adding to a knapsack number or I'm adding to a subset sum number, how come the variable, how come the variable used makes a pseudo polynomial, but the verification is not pseudo polynomial? It's because math is tricky like that, and it just allows that to work. Okay. your input is the 4 sums to represent the solution. So subset sum is some kind of, looking for a sum. Knapsack is also kind of looking for a summation. So you need the sum to represent the solution. I think there's a 0 or 1 reduction that you can go watch to see how that works. It's actually really, really cool. One of my favorite reductions. Very difficult to understand, but when you understand it, it's a sudden realization that's really cool, that you can take something that is, a bit representation and turn it into a summation problem. Consider bit or integer representations. That's what that reduction does. Considering forcing inequalities to converge on an equality, that's kind of what the subset sum knapsack does for us. We are looking for a single equality, but we're going to use 2 inequalities to force it and converge. This is a really cool reduction too. If you have the time, go see it in the book. Output, be sure to convert back to the thing you're looking for. This is true for all transformations, but I think for these type of problems, students tend to forget. In the correctness, again, argue why the summations are equivalent, and then argue if and only if. Okay. All right. So these are the reductions that cross domains. Okay, these are the most difficult reductions that you can come up with. So 3-SAT to independent SAT is a cross-domain reduction. You're going from a SAT problem to a graph problem. Okay, you're going from a SAT problem to a subset sum problem, 3-dimensional matching to 0, 1 equations. These are all what I call them cross domains. They don't start with the same domain and end in the same domain. Okay. So when you go to do the NP proof, it's actually really easy, right? It's the easiest part. You're just verifying if this unknown problem is correct, okay? All right. On the input transformation, what you really should just do is kind of pray about it. It's really difficult. You're probably not going to get it. So just pray that you write down the right words that fit that answer. Same thing with the output, same thing with the correctness. Nothing you can really do, and you're just going to take a fat 0 on the exam, unfortunately. But if I'm being serious, you're not going to get these on the exam. They're way too difficult. They're difficult for me. They're probably somewhat difficult for Dr. Brittle. I had to spend hours with the lectures, with the book open, to just write a general reduction that I could understand. This is not something that you will be expected to do on the exam. Understand them. They're cool to know. They're sort of like the upper limits of what we want students to be able to at least get to the point where they look at it and go, oh yeah, I know some of those words. You've ever seen that meme? That's kind of where you can be, and don't worry too much about this being on the exam. Okay. All right. So that is my final slide on the contents. We are at 4:20. I am going to use the restroom. We're going to give about, let's say, take a 5-minute break, come back at 4:25. I'm going to try to cover as many problems as I can, but if it takes too long, I might just save some of them for later this week, or cover them during the exam prep, which is the next Sunday. I might save some problems because I don't think there's much to cover. As a thing you should know is that I generally do not cover linear programming in any way. It's math. I'm not very good at covering it. It's much easier to write down things that you should understand. So you will probably see that in posts. I'm sure there's already a post. And if you have math questions, ask Dr. Brittle. He's much better at it than me. All right, I'm going to answer 2 questions, and then we're going to take a break. Mahmoud?
Hi, Joves. Sorry. So there was a question in the thread for the office hour about can you? I'll just repost it in the chat just so that you have it. I was wondering if we could just go over this real quickly as well before you bounce off.
Yeah, I'll come back and get to that. Yep. All right. Jafar?
Yep, thank you for everything. You told us that you will not cover linear programming, but I want to ask, will you be able also to share any solution for the problems, the practice problems, or what is the right way of getting some solutions for the exam?
The linear
Or you will
programming
not have
model.
yeah.
The linear programming model solution should be already posted. You should be able to see that. I mean, it's just going through mathematical steps. So if that's unclear to you, I would ask those questions. Like, to me, doing any sort of proofs or any algorithms, it's really cool to get like a visualization of what to do. For math, it's really just like going through the motions and being able to do the arithmetic and know which steps comes next. And so to me, math isn't as it's much easier for me to mess up without really adding value to it, which is why I don't like to cover those topics live. But if you ask questions in the threads, some TA will get back to you.
Okay, understood.
Okay.
But we will have free writing questions on linear programming. So a full problem for 20 points on writing a solution for linear
There will
programming or
be,
no?
you will need to know linear programming, but I'm going to come back. I think we're cutting into a break. I'm going to add 5 minutes, still 5 minutes, so 4:28 we'll be back. All right. Hmm.
Yeah, Joves, I was asking about LP. If you have a full free form solution that we need to do on the exam, or it will be only like those exercises that we have to try to generate these numbers and
I do
something like
not
that.
know. I do not know what will be the exam. Hasn't been started yet, so I do not know. I would not be
And
able to answer that.
from history, usually you had both in earlier semesters or something.
We may or we may not. I don't know. We have had instances where we've had them. We've had instances where we don't.
Wonderful, wonderful.
We're thinking too far ahead. Just try to consume all the different material you have and then worry about it later.
I was thinking like that, but later is in 10 days, so there is no more later, you know. In 10 days
Well,
is the exam
somewhat,
3, so we
yeah,
are already.
the exam has. Like I appreciate and understand your anxiety, but know that I am telling you the truth when I am saying I do not know. I do not have the.
Yeah, I fully understand.
Yeah,
I fully
yeah,
understand.
yeah.
I
I
respect
just have
that too.
exam just hasn't been created yet, so I have no idea. And next Sunday when I do my exam prep, maybe I'll have more information and I'll try to give it.
Yep.
4 more minutes. This next Saturday, I am going to go watch Georgia Tech play Boston College. I am based out of near Boston. I'm in Newton, Massachusetts, which most of Boston College is actually in Newton. And it's because so I'm gonna go watch a game with a couple of other alums. It's gonna be pretty exciting, especially since it's an easy toss-up game for us to win. So no stress going into it. All right, let's get started. So I am going to go over some of the model solutions, homework problems. There was a request. So what is exact solution problem, a decision problem, an optimization problem? Okay, so there are different ways to look at NP and NP complete. There are decision problems, which is to say, given this question, is there or is there not a solution? That's as simple as it gets. Is there a solution? I don't need to know what that solution is. And if not, is there no solution? Right? And that's actually also possible to be complete, even as simple as saying yes or no. And those are not the problems that we typically have in this class. We almost never have decision problems. There's a secondary problem called the search problem, which is given a problem, find a solution. Find a solution that meets these constraints. Those are the problems you will generally see on the written problems. Both on homework exam, you are given a search problem. So given these requirements and a graph, find that solution. The third one, and a really interesting one, is called optimization problem. So optimization problem is less constrained than both the search and the decision problem. And it's basically saying, given this graph, find a solution with the maximum this or the minimum this. So the traveling salesperson problem is typically considered optimization problem. So given this problem, what is the shortest route that hits all vertices? Or given a knapsack problem, what is the best value we can get? So these are considered optimization problems. You can typically change an optimization problem to a search problem just by adding like an additional requirement, like a goal or a budget. So like, for like the traveling salesperson problem, you can say, well, given a path that meets all that touches all vertices, can we do it in under 30 or under 100? Given a knapsack problem with a budget, can we find enough items to create a value of 100? Those changes the optimization problem into a search problem. And so that's the differences. There are some relationships between the optimization problem and the search version, which I think one of our practice problems will go over. And so that's kind of cool. So that's their relationship. So yeah, those are what those three classes. It's not even classes of problem because they're all the same complexity class, except for maybe optimization problems. Optimization problems tends to be NP hard without being NP complete because you typically almost always don't know if a solution is optimal unless you are able to solve for the optimal solution and then compare it, right? For example, if I and this part right here is not going to be NP hard, but it's a good example. If I asked you, is a tree a minimum spanning tree to a graph, right? Because we're looking for a optimization, the minimum spanning tree. And I gave you a tree. I said, is this the minimum spanning tree? There is no known way for you to verify that without generating your own minimum spanning tree and comparing the weights of the two trees, right? So in order to know if my solution is an optimal solution, you have to find an optimal solution yourself and compare it. And minimal spanning trees are in a class polynomial, but that's the same sort of idea. In order to know if an optimal solution is the optimal solution, you generally have to solve for it to see if it's optimal. So that's why optimization problems tend to be in the class NP hard without being in the class NP. But we can do something about that on some questions. All right. Hopefully that answers that. Mahmoud?
Just because I want to make sure I understand, because I also have this problem in my head. So exact solution problems are NP hard, search problems are NP complete, and optimization problems can be NP hard, but not necessarily.
They don't classify like that. They don't classify like that. They're not always like exactly in there. It's better to understand what makes NP complete versus what makes NP hard but not NP complete that way. Now, one of the things I hate the most is that there's no easy term to say NP hard but not NP complete or but not NP, other than to say NP hard but not NP, because all NP complete problems are NP hard. Not all NP hard problems are NP. There is no like single rule that's unbreakable, so I would not try to do that. I would try to understand what the difference between NP hard and NP complete is.
Okay, thank you.
All right. Yep. Shanek?
Hey, Joves. Hello. Quick question.
Hi.
Are all NP hard problems reducible to each other, and are all NP complete problems reducible to all NP hard problems?
All NP complete problems are reducible to each other. All NP complete problems are NP hard. And all NP hard problems can certainly not be reduced to NP complete. That direction doesn't work, because if NP hard problem can be reduced to NP complete, they ought to be. So so the question is, can all NP complete problems be reduced to all NP hard problems? I don't know. I don't think so. I mean, I'm just going to ask the internet. I feel like it shouldn't be.
So I think like NP hard are
Gemini says yes. So
okay.
All right. So
But are all NP hard problems reducible to each other?
all NP hard problems reducible. Gemini says no. Not all NP hard problems are reducible to each other. These are questions beyond my my expertise. I would ask them to Dr. Brittle, see what he says.
Got it. Thank you, Joves.
Yep. No problem.
I saw it somewhere, Jobs, that all NP hard, there is a reduction from NP to NP hard. I saw it either in the lectures or in the book, but I remember I saw it somewhere.
This
all
was
NP problems.
sorry. Go ahead.
Yeah, all NP problems are reducible to all NP complete problems because that is the nature of the NP complete circle. Yep.
Yeah, but same from NP complete to NP hard.
That could very much be true. I do not know. I
Yeah.
would have to look. Yeah, ask Dr. Brito, or I could also do some research and maybe ask.
Yeah,
I
but
do not know.
from my experience, Gemini and ChatGPT are throwing answers like that. So
Right.
I don't know. They don't know what they are saying.
Sure.
Yeah.
I, contrary to popular belief on Reddit, am very comfortable saying I don't know something. I do not know, and I am very comfortable saying I do not know, and you should ask Dr. Brito.
Yeah, that's good from you. Thank you.
All right, let's start working on some practice problems. So our first problem, do I have the right? Okay, homework 9. Let's see. Okay, so this is optimization versus search. I like this problem. Okay, so the question says, recall the search version of traveling salesman problem. TSP input a matrix of distances, a budget B, a tour which passes through all the cities and has length less than equal to B, if such a tour exists. Okay, so that is the search version of the problem. We are searching for an actual insight. The optimization version of this problem asks directly for the shortest tour. Okay, so find the shortest tour, right? And so this is not the full problem statement. I was tricked by the model solution. What is the actual full statement? Show that if TSP can be solved in polynomial time, then so can TSP. Oh, okay. So does everybody remember the? I like this problem because it's actually a method or a approach that you can take. Does everybody remember that I went over the cities and highways problem a while back for graphs?
The Computopia one, you mean?
No, it's called cities and highways.
The homework problem that we need to do the 2 Dijkstra and connect the highway.
Okay, so I need to. I promise this will be related in some way. Because I think going from NP complete to of a unknown runtime to, I mean, a search problem and optimization problem of unknown runtimes is really hard to understand, but this one I think is easier. So the problem as given is the following. So you're given a set of cities along with a pattern of highways, blah, 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 and then you're looking for some capacity that you need in order to travel everything, right? So part B particularly says you are now planning to buy a car and you want to know the minimum fuel tank capacity that's needed to travel from S to T. So the algorithm determined this, so forth, right? And our solution was, well, let's just look for a MST. So hopefully you remember this. Don't worry about it too much if you don't. So our runtime is all of m log n, right? This turns out there's a second solution to this, and it involves binary search. What it does is that, okay, well, we know the maximum road that we have on our edges, right? We know what the maximum road is, and we know what the minimum road is, right? What we can do is we can take the middle, right? Not the mean, but the middle, the median edge, and we set that as our capacity. Now, by setting that as our capacity, we remove, remember our part A was to say, okay, well, if I had a target capacity, I can just remove all those edges and run BFS on it. And that will tell me if I can reach from S to T. It turns out that you can do that over and over again using binary search. So what we can do is we can take the median edge and we remove all the edges that's greater than it. And then we say, okay, run BFS on it. Can we go from S to T? If we can, we then take the median of whatever's left, all the edges that's left, and then we remove all the edges greater than it, and we run BFS on it again. And if we can, we just keep doing that. We do a binary search using BFS. Now, if we can't reach S to T, then we add back some of the edges, right? That is between our median and the previous median. And so we add back edges and we do BFS binary search going the other way, and again, using BFS. You take what you have, which is an algorithm to verify if you can reach S to T. You take all your input, you know you have some max and you have some minimum, and you run BFS against adjusting for that. All of that BFS is all of n plus m, and a binary search on edges is all m. So that actually turns out to be the same runtime. You end up with a all n times log n. Now it's a little bit tricky on the runtime. You can go with this runtime as well, but we assume the cities and highways are connected, and therefore it's all of m times log n. But it's the same runtime. And the way you do it is doing a binary search across all your edges using your verification step. Okay. And that turns out to be the same approach we're going to do for 8.1. Except here, we don't know what the runtime is. We're pretending that our verification or our wondering whether we can pass through all cities with less than equal to m, less than equal to b has a solution. And that if this was in polynomial time, then this also would be polynomial time, because we would take whatever the runtime is for this part, and we would do a binary search for the optimal solution. And this actually can work on a number of any optimization type problems, that if you have a search version of the same problem, you can use the search version to find the optimal solution by enforcing binary search on it. So let's read what the model solution looks like, and hopefully it'll make a little bit more sense because I've shown you what it really looks like on a truly polynomial problem. So now when you are stuck on any of these hypotheticals, it's much easier to just kind of like envision, oh, this is the exact same thing we talked about earlier. So we will show that TSP opt reduces the TSP in polynomial time. The idea of this reduction is to use binary search with B input for TSP to find the length of the shortest TOR. Okay. So let this distance matrix be denoted by D. First, we need to find an upper bound for B, right? So we need to know where remember, binary search only works if you have a lower and upper bound. We've seen this in one of the divide and conquer problems. And so we need to find that upper bound. So what is that upper bound? We need to find the upper bound, what we can do is we can sum up all the distances across the entire matrix, right? Your worst case scenario, your highest bound is to travel every single edge, right? So now we have some upper bound B that is the sum of every single edge across our distance matrix, right? Now we can run TSP with the inputs D and B divided by 2. We say, okay, well, if my upper bound is B and my lower bound is arbitrarily 1, right? Well, let me do a binary search on half of that. Can I find a solution using TSP, the non-optimization version, with this little b set to b over 2? Yes. Okay, then we go the other direction and we check greater than that, right? If not, then we go from 0 to b over 2, right? So we're doing a binary search across what we believe to be all possible solutions. Well, what we know to be all possible solutions. So now we can apply the binary search for a successful iteration. run TSP on the midpoint, on remaining range, blah, blah, blah. And then we continue this recursive process until the range is narrowed to a single integer number, then return the path found by TSP. On this integer, TSP will run all of log B times, right? Because that's your binary search runtime. And then whatever this imaginary, super amazing polynomial runtime we have here is multiplied by log B. Now, if this runtime is polynomial, multiplying it by log B is also still polynomial. And therefore, if the reduction is polynomial, TSP can also be solved in polynomial time. So if TSP can be solved in polynomial time, so can TSP optimization. And I think this is why you can reduce NP hard problems to NP complete problems. Because if there is a polynomial time solution to the NP complete version of it or the search version, then there ought to be a polynomial time solution to the optimization version. And that transformation or reduction is polynomial by the nature of binary search. All right. Any questions about 8.1? Great. Quick show of thumbs up, thumbs down. Did my explanation of the graph problem help with the understanding of 8.1? I was hoping that was like a good way to lead into it. But if not, I can leave that out next time I do it. All right, cool. Okay. Manjunatha?
Just one question. I think you explained it well. So you're saying that the TSP optimization still is in the polynomial time, but you mentioned that if the TSP is a polynomial, has a polynomial runtime, like TSP optimization will have a polynomial runtime, but TSP itself has no polynomial. It's still an NP.
Right.
So okay,
I think this problem is better stated as saying, does the TSP optimization problem have a polynomial reduction to the TSP problem? And the answer is yes, it does have a polynomial time reduction from one problem to another. And that then says, well, okay, if you have that reduction, does TSP having a possible polynomial runtime solution, let's pretend it works, would that make the TSP optimization problem also polynomial? And the answer to that is also yes, because the transformation is polynomial. Therefore, if one problem is polynomial, so too is the other problem. And this is really what you can also kind of see on your A to B reduction, right? You don't know what the runtime to B is. You just know that if B has a polynomial runtime, so would A. And therefore, because of that relationship, B is considered as hard as A. Just like in this problem, TSP is considered as hard as TSP optimization due to that relationship.
Thank you.
Yep. A student asks, we are reducing a harder problem to a simpler one. They actually end up being in the same like general complexity class in terms of hardness, right? They're both NP hard. They're considered NP hard. The difference is that TSP is considered NP complete because you can verify the solution in polynomial time. But the hardness of solving either of these problems is still considered NP hard. And that's also true when you're doing a normal reduction of NP completeness. You're looking for a way to show that A and B are in the same complexity class in its in the solving of its the problem, which is that they're both NP hard. So it's very simple. Right. Gonna move on. Next problem. Stingy set. All right. So this is much more representative of like, a typical homework problem that you'd be assigned or even like an exact exam problem. The previous problem is kind of like a, more of a multiple choice type like, deal like, can you understand the relationship between optimization and search problem? We wouldn't give that to you as a homework or exam problem. This, however, is very similar. So sentry set is the following problem. Given a set of clauses, each a disjunction of literals, so a CNF, and an integer k, and a satisfying assignment in which at most k variables are true, if such an assignment exists, prove that synergy set is NP complete. So proving that synergy set is NP complete involves two basic steps. One, proving that it's in the class NP, which means that we can verify the solution in polynomial time. And two, that we can take some known NP hard, NP complete problem and reduce it to stingy set, okay? One thing that this problem does a really good job of showing is that every single input to your known problem has to be reducible to stingy set. But the other direction is not true. Every single known possible input to stingy set does not necessarily have to be mapped to a set problem, okay? Now, or whatever known problem you end up using. Now, in the grand scheme of things, once we have completed the proof that this is an NP complete proof, there would be a way to prove going the other direction. But for the sake of just proving that stingy set is NP complete, we don't need to worry about what about all these other inputs that stingy set could possibly take that we are not going to cover in the input transformation. We only care about going from sat to stingy set and not the other way around, okay? Yeah. So what is our NP proof? SAT NP verifications or NP proof is generally very basic. You're just checking all the requirements that's stated. There's not like too many tricky things you need to do. So we need to check that it's NP, right? So let the input formula be denoted by F, and let N be the number of variables and N be the number of clauses. Given the proposed satisfying truth assignment S for F, we can check that each clause. So the first thing you also always want to check is that each clause is satisfied. Okay, this takes all of n time per clause and thus all of n m total time. So all of n because each clause can have at most n literals. Okay, there are m number of clauses. You check every single clause against every single possible literal. So it's all of n times m. Then in all of n time, we count how many variables are set to true. Okay. And check if that number is larger than k or not, right? So overall, this is all of n m time in this polynomial. Okay. Any questions about the NP proof? Basically, just check that all your clauses are satisfied by the assignment, and then check any additional requirements are met by the problem statement. All right, cool. So now we are going to do our input transformation, right? So remember, your input transformation only has to satisfy the stingy set part, right? And if stingy set says, okay, well, I have k variables that can be set to true, and my sat or 3sat, whatever sat you decide to use, I think you're only allowed sat and 3sat, says, well, I don't really care how many variables are set to true. I can potentially want all of them set to true. So what do we need to make this possible? Well, I can simply ignore the restriction of k by setting k to n. If k is set to n, that means every single variable is allowed to be true. Now, I can have less than n variables be set to true, but that's not what the restriction was trying to prevent, right? At most k variables does not prevent less than k variables. So by saying, give me the maximum number of variables that I can possibly set to true, I have done just that. So let's take a look at our transformation. So we're going to set k to n and give it a stingy set, right? And so then the stingy set returns no, then return no for sat. And if stingy set returns a satisfying assignment, then that is actually as is the solution to sat, okay? You know, every time I ask for this to be fixed, it does not get fixed. All right. I do not like giving the runtime separately from my input-output transformation. I think it's hard to read. It causes you to forget. So I will always give my runtimes to this. This is all one because I'm just setting a variable. This is also all one because this is how we're doing no transformation. Okay. So a justification is then clearly every assignment over n variables will have at most n variables set to true, right? So this is just a truth. So this actual restriction will not constrain our set of solutions. Then the stingy set returns a satisfying assignment is the exact same assignment for the original SAT. And then likewise, if stingy SAT does not have a assignment, we don't have a solution for the SAT solution, right? So the only transformation is doing that. So it's O1 and the second part. Okay, well, it doesn't give me an output transformation time, so this unfortunately would be a -1 if graded. I will hopefully once again try to get the team to correct this solution. I do not like the way the solution is written, but that is the approach that the solution is taken. Any questions about how we go from SAT to stingy SAT? And I think a student asked if you can use 3 SAT as well. That's fine. That would also work the exact same way. All right. Move on to the next problem.
Sorry, Jovis, sorry.
Yep.
If we do 3 SAT though, we have to go through the whole process of converting this into a 3 SAT the same way that SAT was converted to 3 SAT, or because we...
Nope. Your 3 SAT is the problem you start with. So your 3 SAT is what's constraining the input into 3 SAT. So every input to your 3 SAT will be the right format. Going from 3 SAT to stingy SAT is perfectly fine with every clause being 3 or less literals. There's no restriction in either direction. So you want to, there's nothing that you need to do.
Understood. Okay. Sorry, I confused the directions. My bad.
Yep. You only on the transformation side, you only need to worry about your black box requirements, not your input. Your problem that you've chosen, the A problem. You don't need to care about the restrictions there because the input in there will automatically already fit that format. Okay. Cool. All right. Next problem is click 3. Okay, so click 3 is also not a problem that you would typically see because it's trying to get you to see what the mistakes are. So this is not a very this is not a reduction that you will see on the exam, but we will talk about it because I think it's pretty good. All right. So you're asked to solve 3 parts. So consider the click problem restricted to graphs in which every vertex has degree at most 3. Call this problem click 3. Prove that click 3 is in NP. Okay, so this actually is kind of similar to your reduction. So we're just going to prove that's NP. Okay, so we are going to get a graph and a goal G and a potential solution set S, right? It is easy to verify whether S is a click by checking all pairs of vertices in S are connected, right? So this is your standard click check. Anytime you need to check a click, just say, check if all pairs of vertices are connected, all of n squared. No additional details, but you have to give the statement, right? And then you just need to check that the size is greater than equal to G, right? So you have your goal, and you have to check if the solution is set is greater than your goal, and that takes all of n. Okay. Now notice how in here I don't do any verification of my input. I assume my input is true, right? I assume that when my click problem is restricted to graphs in which every vertex is degree at most 3, that my input fits that requirement. I don't have to go in and check all that. Okay. So you only have to check the output or the proposed solution is valid. This ends up being the exact same verification for click in general. Okay. B, what is wrong with the following proof of NP completeness for click 3? We know that click problem in general graphs is NP complete. Okay. So it's enough to present a reduction from click 3 to click. Given a graph G with vertices of degree less than or equal to 3 and a perimeter G, the reduction leaves the graph and the perimeter unchanged. Clearly, the output of the reduction is possible input for click, right? Furthermore, the answer to both problems is identical. Sure, this proves the correctness of the reduction and therefore NP completeness of click 3. So what is wrong with our reduction? The reduction is in the wrong direction, right? And this clearly shows why going in the wrong direction is not beneficial to the proof. I can make an easy problem hard, right? An easy problem using a hard black box is not special. It's not going to do anything to prove that my easy problem is either easy or hard, right? So in this particular case, because I've gone in the wrong direction, going from click 3 to click, I don't know the hardness of this problem at all, okay? We want to prove that click 3 is more difficult problem. To do that, we'd have to do it the other direction, okay? We'd have to somehow go from click to click 3, okay? That's not what the proof does. All right, so we're gonna try again. Part C says, it is true that the vertex cover problem remains NP complete even when restricted to graphs in which every vertex has degree at most 3. Okay, well, let's take that as truth. I think it's like shown somewhere in the book. Call this problem VC3. What is wrong with the following proof of NP completeness for click 3? We present a reduction from VC3 to click 3. Okay, correct direction at least this time. That's good. Given the graph G equals VE with no degrees bounded by 3. Okay, because that's what our VC3 is claiming. And a parameter B, we create an instance of click 3 by leaving the graph unchanged and switching the perimeter to be V minus B. Now, a subset C of V is a vertex cover in G if and only if the complementary set V minus C is a click in G. Therefore, G has a vertex cover of size less than or equal to B if and only if it has a click of size greater than or equal to V minus B. This proves the correctness of the reduction and consequently the NP correctness of NP3. Okay. This reduction is also not correct, right? Because it makes a false statement. It's the right direction, but it makes a false statement. It's saying that a subset of C from V is a vertex cover in G if and only if the complementary set V minus C is a click in the same graph. Okay, that's not correct. It is what the correct statement is that a subset is a vertex cover in G if and only if the complementary set VC is a click in the complementary graph, which is V, which is G is equal to V, and all the edges that are on the up. Like if E exists in the original graph, it does not exist in the updated graph. If E does not exist in the original graph, then it does exist in the updated graph. So you have to invert the graph basically. The complement of G is not guaranteed to retain the property that every vertex is degree of 3, right? Because if you have a vertex that has, let's say there's 100 vertices, right? A vertex that has 3 degrees, when you invert it, it loses those 3 edges, and now 97 edges get added. So now that vertex has 97 edges, and it's definitely not okay for that to be an input to click 3, right? So the inversion of your graph changes the node count between the two types of problems, and therefore it's not useful for this desired reduction. If this confuses you, go watch the lectures. I believe the lectures has a vertex cover to click or a click to vertex cover. Either way, it tells you that it is using the inverse of the graph, not the to set it correctly. Okay, Manjanatha?
Joes, if we could scroll up a little bit, the part A question, where is that goal coming from? It is not part of the original problem statement, right?
This goal?
Yeah.
Because the click problem has a goal, therefore its updated version of at most 3 would also have a goal. It's just basically adding one requirement to the click problem, and the click problem has a goal.
Okay, so what if
it's
we
saying
don't
take
have
this
a
problem
goal?
that we know about, add this additional restriction, and so you have to know what that problem that we know about consists of, one of which is a goal.
Okay, and what if we don't add a goal here? Then it will become trivial, is it?
If you don't have a goal here, it becomes an optimization problem. and it's still NP hard, but it would not be NP complete. You wouldn't be able to confirm it.
Okay, thank you.
Yep. Right. Question in chat: can we arbitrarily add remove goals to NP hard problems? You cannot. You have to find a way to satisfy them. So if the problem that if the A problem has a goal, you have to be able to satisfy it. If the B problem has a goal or budget, you have to be able to satisfy. So you have to satisfy it on both ends. You cannot just remove them. You can make them trivial, like stingy sat, where we said, you need to have at most k variables set to true. You can make them trivial and not a restriction anymore, but you do have to satisfy it. Okay. Let's see. Next problem. Exact foresat. All right, exact foresat. I'm going to use my solution. I think my solution is typed out better and easier to read. But feel free to use it to match the solution that the model is. This is 8.8. Guess it's not much easier to read. Yeah. Okay, let's go with the full solution. I don't want to confuse you. Okay. Exact foresat is saying, in the exact foresat problem, the problem is a set of clauses, each of which is a disjunction of exactly 4 literals. So a CNF with exactly 4 literals per clause. And such that each variable occurs at most once in each clause. So you can't have the same variable twice. The goal is to find a satisfying assignment if one exists. Okay, so prove that exact foresat is NP complete. So we're going to call this foresat E4sat for easier writing. And we assume there are n variables and clauses, and each clause has exactly 4 variables. Okay. And again, the NP proof of this is generally pretty simple. I actually think the NP proof on these problems are basically, for the most part, a free 4 points that if you just go and check off every single requirement and check each one, you will get 4 points on this problem. You should not lose 4 points on these type of problems. It's the way I see it. First, we need to prove that E4sat is in class NP. So that means that we need to show we can verify it in polynomial time. Given the Kinder solution of truth assignments in each variable, it takes one time per clause to verify that that at least one literal is satisfied. Because when we used to take O of n times m, we have a variable size n, right? But if every clause is exactly size 4, then it takes out O of 4 times m to verify every single clause. And O of 4 times m is the same as O of 1 times m, which is O of m, right? So your runtime here is O of m, right? And you can verify all the assignments in that. Now, what happens if you do O of n times m here? Well, it is wrong. The runtime here is wrong, even though O of n times m is a perfectly okay runtime to do this. It does not match your statement. It does not match what the runtime is to verify all these clauses. Now, if you wanted to say, instead of checking to see if one of the literals is in the assignment, you wanted to take every single assignment, right, and check to see if it's in the clause, therefore blowing up your runtime to O of n per clause, and you do that m times, and now it's O of n times m, that's okay. As long as you give the steps and the right steps to give a correct solution that matches the runtime you are claiming, it's okay. You just can't, give a runtime that's wrong to the steps you're taking. Okay? Any questions on the NP proof? Cool. Oh, yep. Jonathan?
About the timing. So although there are 4 literals in each clause, but your assignment solution is could be n number of literals, right? Or variables, sorry. So each time for each class, you still have to go through all the n variable assignments, right? So it will not be big of one, isn't it? For each class?
The assignment output of a SAT problem is considered to be an array of true falses on each variable. So it would be like, oh, I'm looking to see if A is true or false. So I can index into the array as true
indexing. Okay, gotcha.
Yeah.
Thanks.
Now, if you want to say, I want to consider my assignment to be a set of literals that has to be traversed in O of n, you can do that, and then you can give that as an O of n times m runtime. Again, if you're unsure about something, just make it slow. Force it to be as slow as your runtime is correct, and that's the best solution.
Thank you.
Yep. All right. So let's do the reduction and talk about it. All right, so the reduction here can be a little tricky. So
hey, Joves.
Yep.
Just a real quick question here. So in these type of problems, right, and for SAT problems, we don't need to verify size at all, right?
What do you mean by verify size?
Like if it's exactly like 4.
No, because that's the input. Any input restriction, you don't have to verify. You only have to verify the output or requirements for the solution. There is no size requirement for the solution, so I don't care about it. I do not need to verify the exactly 4 literals.
Okay, sounds good.
All right. We're gonna do some tricky Boolean algebra equivalency lessons. So this is a hard one. This is not something that would be easy for you to just like see for the first time and solve. But hopefully we get there. All right. So we take our formula 3SAT. So we want to use 3SAT here because we want to limit the number of transformations we have to do. You could potentially do SAT here, but it would be a much more difficult reduction. Now, that's one thing you should consider is that everything that's NP complete is reducible to everything that is NP complete. You can literally pick just one NP complete problem and use that for all your reductions. Now, some of them are going to be extremely difficult and some of them are going to be extremely easy. You want to learn all the different ones so that you can try to find the one that's easiest. Okay. All right. So we're going to take a 3SAT. Okay. We're going to compose C is a clause of 3 literals. Okay. So if these 3 literals are what my clause is, we're going to create a new variable W and replace C with a pair of clauses. So C prime is now equal to X or Y or Z or W and X or Y or Z or not W. Notice that the extra variable W here, right, cannot be used to satisfy both clauses. If I set W to true, this one has to be false. If I set this one to true, this one has to be false. I cannot set W to anything that would satisfy both clauses. So no matter what I set W, X, Y, and Z has to be satisfied as is for one of these clauses. I set W to true. I don't care about this anymore. X, Y, or Z has to be set to true. I set this to true. I don't care about this clause anymore. X, Y, or Z here has to be set to true, right? So either way, no matter what W is set to, the full original clause has to be satisfied. Okay, so we show the equivalency of this clause to these 2 clauses. We do it for any literals that has 2, right? We add 2 new variables, W1 and W2, and we replace C by 4 clauses. So X or Y or W1, W2. X or Y or W1, not W2. X or Y, not W1 or W2, and so forth, right? So once again, the combination of these 4, no matter what you set to W1 or W2, at least one of these clauses has to be satisfied based on what the original logic was, okay? So let's say W1 and W2 are both set to false, right? So if these are both set to false, then this one can't be satisfied, right? These are set to false. These can't be satisfied. X or Y has to be satisfied correctly. This one will be satisfied. This one will be satisfied. This one will be satisfied. We ignored these three and we figured out what X and Y should have been based on this clause, right? If X and W1 and W2 are set to true, right? Then this one we don't care about. This one we don't care about. This one we care about. W1 and W2 here are both false. So therefore, X or Y here has to be
Sorry,
set
Joves,
correctly based on the
are you
original.
writing something on the screen? Because the screen isn't
No, I'm
showing
just-
anything.
No, I'm just going around with my mouse. Can you see my mouse movement?
No.
Let me I want a pen. This one? Yeah, okay. Can you see this?
Yeah, okay.
This?
Yeah.
Okay. So I'm not actually writing anything. I'm just saying, okay, well, if these two are both set to false, right? Then this one, this one cannot be set to true based on W1 and W2. All of these don't matter to me, right? But I still have the original X and Y here that needs to be satisfied. Similarly, if I set these to set these to false, or true. Yes, that's true. Then these don't matter to me, and then only this part right here matters, right? So no matter what I set W1 and W2 to, any combination, one of these clauses will represent the original clause logically, okay? So any combination of true statements in the two new variables can satisfy at most 3 of the 4 clauses, and therefore I am going to represent this, okay? We add so similarly, if C has a single literal, we add 3 new variables and replace it with 8 clauses. It gets a lot bigger. We're not going to do that. We've shown the logic here, and this part you can just kind of believe me on it. So that F prime will have at most 8M. So at most, I'm taking the same clauses and I'm creating up to 8x additional clauses. So that gives me O of M. And then n plus 3, because at most I can only add three literals, right? I'm not going to add more because it's a 3 sat. Therefore, it's all of n variables, and therefore the input transformation takes all of m time. Yeah, because my variables are not going to. It's going to change, but it's not going to. It's still going to be all n variables. So it's all of m time to do this transformation. Okay. Now the output transformation is to report no if I get a no. But then if I get, if I have a solution, I'm just going to remove the added variables and return the true statement for the original variable. And then that is all n time because all I'm doing is updating the assignments. Okay. My correctness justification then is that we have argued that the clause-by-clause basis F is satisfiable if and only if F prime is satisfiable. So this is what I mean by arguing the equivalency. I've argued clause by clause that they are equivalent. It is an equivalent logic between my original F and my F prime. Okay. Therefore, I can say, okay, well, if F prime has a satisfying assignment, then F has a satisfying assignment. Okay. And therefore, my entire thing is shown to be NP complete. Eduardo, question?
Can you repeat one more time? Why is it for the input transformation? Why do you end up with OM time?
Yeah. So we agreed that when I have a clause of 3 literals, I double the number of clauses, right?
Right.
And if I have a clause with 2 literals, I get 4x the number of clauses, right?
Right.
And then I kind of hand waved it, but I didn't want to write out all the things that if I have a clause with only 1 variable, has a single literal, we add 3 new variables and we replace C with 8 clauses, right? So
Sure.
if every single one of my clause has only 1 variable, at most I'm adding 8 clauses per clause, and therefore it's all of 8M, right? For every clause I have, at most I can create 8 new clauses, which is 8 times M, and because 8 is a constant here, it simplifies to all of M.
Got it. Thank you.
Yeah. And here, so one of the things that's not super clear here is that I can reuse these variables. I can reuse W. Here should be W1 and not W1. W1, and then here's W1, W2. I can reuse these across all my clauses. They do the same thing. I do not create new variables for every single clause, right? And so if I have a single literal, I have 3 new variables. So at most, I need 3 new variables total. And therefore, it's O of n plus 3 and O of n variables. And so this 3 is a constant. So this runtime right here can be discounted, and all I care about is updating my m clauses, my all 8 m clauses. Okay, Shinek?
A quick question. If we don't reuse variables, it's fine, right? As long as we can capture the runtime properly.
Yeah. If you don't reuse the variables, you have at most of 3 additional variables per clause, right? So then
so
it's
it's still
O of 3m. So it's O of 8 plus m plus O of 3m, which is O of 11m, which is still O of m. Yep.
Gotcha. Okay.
Yep. All right. Any other questions
Sorry.
about exact force? Yep, go ahead.
Sorry, one quick thing. I couldn't follow. So so this addition of variables like O of n, like somehow here we don't say the runtime is O of m plus O of n. Do you mind explaining like why it's O of m?
Right here?
Yeah, in the input transformation.
So I'm updating up to 8 times the number of clauses I have. When I add 3 variables to my number of variables, this is a constant. So I can just drop this entirely. Like this plus 3 is a constant to add that many variables to, I guess, to my input. So it's just basically saying this part doesn't really matter. The input transformation is dominated by O of m.
Okay, I follow. Thank you.
Yeah. Like what is the runtime to add 3 variables? All of 3, right? Is all of 3 going to be greater than O of m? No. So you can just drop it. All right. Bing?
Yes. A quick question on formatting. Since we can only use plain text in the exam, if we have to deal with a lot of not in the answers, what's the preferred way to say that without causing confusion?
I'd like to use the explanation point.
Okay, thank you. And do we need to wrap, like say if it's W underline 2, do we need to wrap that? Or it's okay to just do exclamation point W2?
I like to do explanation and then.
Okay, perfect. Thank you.
And it's like, we're not going to hold you to like, oh, we're not going to give you rich text, but you have to be held to some standard. Like as long as it's obvious, like if I read that and I go, oh, that obviously means not W underscore 2, or not, you can also do not if you want, right? Or you can do like underscore W2, like anything that's reasonable we'll take, as long as it's not like, ooh, this takes like a conversation between me and you to figure out what this means. It's generally acceptable.
Thank you.
Oh, Tim has suggested this as well. That also works. Yep. Mahmood?
Yeah, so couple of questions. You're because so you're saying it's n plus 3, right? Why isn't it n times 3? Like, why are we only adding and not multiplying?
So it wouldn't be n times 3 because you don't like the number of additional variables you add here, right? Does not care how many variables you have. It cares about how many clauses you have. So if you weren't resetting the variables, if you were just reusing them, you need only 3 variables to take care of this. If you somehow decide, if you didn't see that you don't need to use new variables and you think, oh, every time I have a clause, I need to use up to 3 brand new variables, then it would be all of 3 times m. It would not have anything to do with how many variables you have. It's dependent solely on the number of clauses.
I think I get it. I'll rewatch, and if I have any questions, I'll post in the chat. Thank you.
Yep, no problem. All right. Bing?
Or I have one more question on the magnitude. So if in a question it's not very clear m is greater than n or whatever other letters or symbols or signs, then when we do the sum or overall, should we include both in the overall?
No, because I'm not doing anything with it. That's the point I'm getting at. Like I don't care I don't care how many variables I have. I only care about how many clauses I have. I don't know if m is bigger than n or not. I don't really care because n does not do anything to the number of additional
I know in
variables.
this case that's the case. So it's only OM. It doesn't matter how big OM is. But I'm just saying in general, if a question when you do runtime analysis, both n and m appeared and it's not clear the magnitude. So in the overall, should we include both?
Yeah, I could potentially have more variables than I have clauses, or more clauses than I have variables. So neither of them are strictly larger than the other. So yeah, so I would include both if I have to.
Okay, thank you.
Yep. Okay. Moving on. Subgraph isomorphism. All right. I like this problem. All right. So this is called proving NP completeness by generalization. So students are going to ask, what does generalization mean compared to other things? Generalization is sort of a way to describe if the reduction is pretty easy. The reduction generally means that I can take one problem and turn it into the equivalent of another problem through a few transformations. And now I can argue, well, if and only if is simple, right? Because I've made the two problems exactly the same thing. That's what generalization means. And you don't have to worry too much about it other than the idea that generalization exists. Because when you are presented with a written problem, either on the homework or on the exam, we expect the full proof. We expect you to tell us the NP proof. We expect the input transformation, the output transformation, and the correctness. So you are expected to write a full proof regardless of how simple the transformation is. You can think of generalization as like, okay, well, if I give you this problem, what is the problem that it is most similar to that you can do a reduction to, such that the two problems can be shown to be equivalent, and therefore they are both NP complete. But we are going to write the full proof because that's what we expect of you, and that's what we want to show. Okay. So the question is saying, given as input two undirected graph G and H, determine whether G is a subgraph of H. That is, whether by deleting certain vertices and edges of H, we attain a graph that is up to a renaming of vertices identical to G. And if so, return the corresponding mapping VG into VH. All right, that means for a given solution that we're trying to verify, we have some input graph G, and we have some input graph H, and we are going to also have a mapping to go from one to the other. Okay. Yeah. So that is problem statement. So NP proof, which again is hopefully mostly 3 points because you can be as simple and brute force as you want. You just need to verify all the different parts. Okay, so now we're given a G and we're given an H and given a mapping, say pi, from V to V prime. Okay, we can verify the solution by traversing graph G, and then for each vertex in V, check if V pi V is equal to pi prime exists in H, right? So we are checking to see that every single vertex in one graph it exists in the H graph, given the mapping, okay? And then for each edge VU adjacent to V, okay, so if it exists, if the mapping exists, check all of the edges adjacent to V prime to see if one is V prime U prime, and traversing the original graph takes O of V plus E, and at each edge we have E prime edges to check, yielding O of V plus E times E prime, which is polynomial. Now, this actually, I don't think is a very optimal solution. I don't think V plus E times E prime is optimal. I think it's actually probably easier or more optimal to turn these into adjacency matrix and then just do a really quick check instead of traversing through all the possible edges in E prime. But it works, and this is a solution that we took. So that's fine. All right, we have questions. Anika?
Yeah, so I wasn't sure how this one works because if you have a vertex that's connected to another vertex, but you don't include that one in the subgraph, then do you also not include that edge? And does that count as a difference between the two?
So a subgraph in this case is that all of the vertices. So you take the mapping and you only consider subgraph. That subgraph exists in both graphs. That means all the vertices are mapped from one to other, and all the edges between those vertices exist. It's called
So
yeah.
yeah, so if you have a vertex that maps between the two, but it has an extra edge in the other graph, but you're not counting that edge in the subgraph, does it still count as the same subgraph?
What did I delete? Sorry. I don't believe that there can be additional edges. I believe that the edges between the induced subgraphs have to be a match.
Okay, so do you
Because
also
you're
that in your NP proof? Like if you have A, B, C in one and like, some the other three in the other one, do you need to check that there's not another edge from like A to D in one of them? Something like that?
Hold on. Given as input two underwrite graphs, determine whether G is a subgraph of H. Oh, G has to be a subgraph of H. That is whether by deleting certain vertices and edges of H, we obtain a graph that is up 3 nanometers. Okay, never mind. I take that back. H can have extra edges that G does not have, but every edge that G has, H must also have a corresponding edge too.
Okay, that makes sense.
I take that back. This is not a induced subgraph. This is just a subgraph. So we're going to take every edge adjacent to V, check all the edges adjacent to V prime to see if one is V prime, U prime. So H is the original. So VU here is from G. Check all edges adjacent to V prime to C. Okay, so we are checking that every edge we have in G has a corresponding edge in H. That is correct. Yep. All right. That is exactly what I hope that is it. Okay, cool. Shanak?
Hey, quick question. So I think the part of the NP proof is verifying that edges in G exist in H or
yes.
for a given mapping. So as we are traversing the edges in G, could we then also verify the corresponding edge in H by looking up the two endpoints and doing an O of N traversal in the larger graph?
I don't want to get into too many like, can we do it this way instead? Like if the way you think makes sense, post it in the practice bits and see what other students think. Yeah. Because there's like unlimited solutions to this. Yeah. Mahmoud?
Yeah, I don't quite understand what the mapping is exactly. Is it like in G, a node is called A, and in H, a node is called.
So basically, you have a graph G. Right, we call this A, B, C, D. Okay. And I have another graph here. And I want to know if this red graph here is a subgraph of this black black one. So I have a mapping that says okay. So I check to see, okay, well, here's my A. Do I have a mapping from A to some vertex here? E. I do. Good. B, C, and D. Yep, I have a mapping to every single vertex. Now, I look at A, I go, okay, what are my edges from A? Well, A, I have an edge from A to B, and I have A to C. Okay. Then I go to my corresponding E, and I go, okay, do I have an edge from E to F and an edge from E to G? I could have more edges than that, but I need at least one edge from E to F and E to G. Yes, good. Then I verify that. So I go through all my vertices, I verify all my neighbors, and I verify here that the same equivalent or the same the mapped vertex has a edge that is to the equivalent neighbor. So that's what I'm doing. So my output is really this thing right here. This is the mapping, aka pi, I think is what we call it in the solution.
Understood. Okay, and then my second question was, so here you're saying the runtime is O of V bar plus E bar, or the magnitude of V plus magnitude of E times the magnitude of E prime. But I know that we were said not to use the bar notation, so how would we write this out in the exam?
So the reason why we don't typically use the bar thing is that we think N and M is easier. But here, M could represent two things. So the way you could potentially write it if you wanted to is you can say, you'd have to declare it, which is I think the thing that this solution is trying to avoid. If N equals magnitude of V and M equals magnitude of E, and then M prime equals magnitude of E prime, right? Then I can say it's O of N plus M. It's just that, generally N and M are accepted to be like the number of vertices and the number of edges, and we think it's much easier to sort of work with. But what happens when you have two sets of edges and two sets of vertices? Well, then it's just easier to use the magnitude of the actual vertex variable and the edge variable.
So
if you wanted to
sorry, go ahead.
If you wanted to declare what they are, then you can get to this part, and that's fine if that feels better.
So in both cases, using the magnitude symbology or specifying that M prime is the magnitude of E prime, both of those would be accepted in the exam?
Yeah, if you make it clear. If you just ended up here, this is what you have, I have no way to know what N and M prime represents. Because there's multiple sets of vertices, multiple sets of edges. I have no idea what this means.
Understood.
But here, where it says, we have E prime edges to check, you can right here say we have M prime edges to check. You've declared what the representation is, and then you can use it.
Gotcha. Okay.
Yep. Right.
Thank you.
No problem. All right, let's go to the input and output transformation. All right. So input transformation is that we are going to abuse the idea that a click when you remove an edge from a click, what you are left with is a smaller click. And if you remove another edge from that click, you are left once again with a smaller click. Because all vertices attached to all other vertices, any edge removal leaves you with just a smaller set of vertices that's attached to all other vertices, right? So you are left with a smaller click. So if we take the input of click, right, and we set that to h and an integer k, because that's what our input to click is, we construct an input to subgraph isomorphism. We let G be a complete graph, so every pair of vertices is connected by an edge, where the number of vertices is equal to k. Run subgraph isomorphism on G and H. This input reduction takes polynomial time, which is since it creates a complete graph with k vertices and O of k squared, which is equal to O of v squared, and k being bounded by v prime, the number of vertices in H. Okay, so that is our runtime, our O of v prime squared. Okay, output transformation returns no. Otherwise, for each vertex v of G, use the return mapping to locate each v prime equals pi v, and then return the set of such vertices as solution for click. Okay, this is all v time in this polynomial. The reason why this works is because in order for our input to click to have a subgraph isomorphism to a click is for the graph itself to have a click of that size, right? Because if it doesn't have a subgraph of that size that's equal to the click we are talking about, that we have just manually created, then that click can't exist at all, right? So then the correctness justification is if the click has a solution, then there exists a click of size G and H. And by creating a G size click graph to pass it as our G, we know that subgraph isomorphism must have a solution with G and H. It must find that click. If click does not have a solution, then there is not a click of size G and H. Therefore, subgraph isomorphism will not be able to map a click graph within H because we are asking for it to find a graph, a click subgraph, and if it doesn't have it, then it can't map it. Okay, and therefore you have your reduction. Any questions about this particular reduction? No? Wow, really good. Good job. Cool.
Sorry, Joves, I didn't.
Yeah.
It took me a while to reach the mouse.
Yep.
So we're saying that we're given the input H, which is
Yep.
the graph, the full graph that we want.
Right.
And then we're creating a G.
Yep.
And then we run the subgraph. Sorry, this is where I'm getting a little lost here. How does creating a complete graph could potentially prove this? I'm a little confused here.
Yeah. So I start off with a graph of unknown. I do not know what this graph looks like. Okay. I am looking for a K click. Okay. That is what my click problem is doing, right? What I'm going to do is I'm going to get, well, I don't know if the K size click here, but I will take the same question mark and I will set this to my H. Okay. At the same time, I am going to set my G to a K size click. So I don't know how many vertices I need. I'm going to just pretend it's 5. Right. Now I am telling my subgraph isomorphism, find this subgraph in here. Right? Well, how is it going to find this subgraph in here? Well, if this subgraph is a K-size click, it's saying find a K-size click in here. That's exactly what it's asking it to do. Okay? So it's equivalent to saying finding a K click in this question mark. It's the same thing as saying, well, I will draw this K-size click for you, but also find it in this H. And it ends up being the same problem.
So if I understood you correctly, we're creating a k-size click, which is
Right.
G, and then we're saying,
Right.
hey, find it
Yep.
in H using the subgraph isomorphism algorithm. If it
Right.
returns true, like it returns a
Right.
click, then we just return that click as the solution to the click algorithm. And if it can't find it, then there's no click that exists with size K.
Right. After doing the remapping, because we don't actually know where the click is, so I don't actually know what the names of the vertices in here will be. I'm just arbitrarily naming them, which is why I need the mapping. So I will map
The
it back to
subgraph
the
should
original graph.
return the click though, right?
The
Sorry, should
subgraph
return
is gonna
the return the mapping. Sorry.
mapping, right? So then you have to map it again as a proper output to the click problem.
Oh, I see. So it returns the mapping. So we use the mapping to find the click in H, and then we return that click.
Yes.
Okay, cool. Thank you.
All right. Cool. All right. So I am going to cover the two problems I think that's in homework 10. That is okay. That is NP complete. And then there's LP problems, but again, those are best covered in Ed. So go ask questions there if you don't understand it. All right. So this is a set problem. So we have a heading set problem. Heading set problem. We're given a family of sets S1, S2, ... Sn, and a budget B. And we wish to find a set H of size less than or equal to B, which intersects every Si, if such an H exists. In other words, we want H intercept Si to not be the empty set for all I. Show that heading set is NP complete. Okay. Go over the NP proof real quick, because that's always the free 4 points as long as you're paying attention. Right. So we show that the heading set is NP. So let M be the number of unique elements. Okay. Again, M here has no meaning unless you assign it. It's not a obvious meaning. So you have to say what M equals. The number of unique elements. So for S1, S2, ... Sn, and a budget B, we first verified that the size of H is less than or equal to M, which takes all of M. Now, you might say, well, we weren't given M, we were given N instead. How do you justify using M as a runtime without it being considered a pseudo-polynomial? M here has very explicitly been tied to some aspect of the input such that a size can be determined. I know that I can scan the entirety of my my sets and determine how many unique elements are in my sets and assign a value to represent the size of that set. When M increases, like if I added more unique elements to my thing, my runtime will increase. And therefore, those unique elements have a space to it. And therefore, I can assign M to it and then justify my runtime like that. M here is not an arbitrary or is not a number to be used for magnitude. It represents something about my input, and that's allowed. Okay. So then we make a Boolean array A of size n, one for each subset, initialized to false. This takes all of n time for each number H in H, H in big H. Do we assume it's number? Okay, it's not a number, but for every item in H. We set A of I equal to true, okay, where H is some element of Si. This takes all of nm squared. So basically, I am going to just set all the things I find to true. Okay. Set each of my subsets to false, and then if I find it, find A intersect, I set it to true, right? It's all n times m squared because I have n sets I need to verify. Each set I'm trying to verify has at most m unique elements. And my heading set that I'm trying to verify also has m up to m unique elements. So it's m times m to check the intersect between two sets, possibly, and I have n such sets to check, so it's all of n m squared. Finally, check that all entries in A are set to true, which takes all of n time. If so, the candidate solution is valid. Otherwise, it is not. Overall, it takes all of n m squared and is polynomial. Thus, heading set is in the class NP. All right. Questions about this NP proof? Shanak?
A quick question. So in the NP proof, are we supposed to also explain under what conditions the solution is valid versus not valid, or is that understood based on the requirements in the problem statement?
Sorry, what do you mean by valid versus not valid?
So finally check that all entries are set to true.
Yeah.
And if so, the candidate solution is valid. Are we expected to like list out all cases in which it may be valid or like may not be valid? Or is that
No,
understood
it's just-
from? Okay,
It's
got it.
understood. The solution, what the solution you're looking for is explained to you. You don't have to re-explain it back to us.
So then the goal of NP proof is to show how we can verify it is a solution in polynomial time, not justify that it is a valid or invalid solution. Or
Yeah,
or
you just
explain
have to-
when it
yeah.
is. Yeah, okay, got it.
Yep. All right, cool. Another hand, Mahmoud?
Yeah, sorry, maybe I missed it, or maybe it didn't click with me. Why is it m squared again? Like, why is it n m squared?
Yeah. So you have some set of things that are in your, so this is my H, right? Right. And we declare that this can be at most O of M size, right? Because that's how many unique elements you have across all your sets, and therefore cannot be larger than O of M because you're not going to have more items than the unique item. You could have less, but your maximum is going to be O of M.
Mm-hmm.
And then your S1, some number of items. Your S2 equals some number of items. Right. And then dot dot dot, you have Sn, right? So you have n of these, right?
Yeah.
Now, what is the maximum size that each of these sets can be? Well, each of these sets can at most have O of M, right? It could potentially have every item and every unique item in this set, right? And so this is also O of M, right?
Mhm.
Okay, now how long does it take
Oh,
to
I
verify
see
if
it.
one of these items is in one of here? Well, I'm gonna go, is A in here? A, is this A? Is this A? Is this A? Is this B? Is this B? Is this C? Potentially, I could have all of M items, and I check the last item, and I check the very last item here, and those are the match. Everything else is not a match, right? So potentially, this could be O of M times O of M. Okay? To check each set, it's O of M times O of M. I have N sets, so now it's O of N sets times the O of M check. That can happen. Right? So this is O of M squared.
Thank you.
Okay? I'm running out of water. My voice is leaving me. Hopefully I can finish this. All right, so now we do a reduction and explain why this works. All right. So you can consider this to sort of somewhat be cross-domain, but I find sets to be sort of in this gray space where it's kind of it's kind of related to SAT problems. It's kind of related to graph problems. So don't think about seeing like a set problem like this and saying, oh, this is something that Joves said can't happen. Set problems specifically live in a gray space that's very adjacent to all the other type of problems. So vertex cover to hitting set is very valid in terms of exam difficulty. Okay. So our input transformation is that we're going from vertex cover to hitting set because vertex cover tells us that a single vertex can cover many edges, which is similar to how a single element, right, can cover many sets. And so we're looking for a small number of elements to cover all the sets. Hence, we are looking for a small number of vertices to cover all the edges. And so for a vertex cover, we're going to create a set UV, right, for every edge that we find. Okay, and we set S to be the family of all these sets, and then we pass S and B, which is the same B as the original problem for vertex cover, into hitting set. It takes all of n plus m time to create S and is polynomial. Our return is the hitting set returns no if it doesn't have it. Otherwise, we return H as a solution to vertex cover. We return the exact answer as the vertex cover. It takes all of one, return the set as is, and is polynomial. Okay. The reason is if a solution to vertex cover exists of size B contains, there exists a set of B vertices which hit every edge. Because we have mapped each edge to G as a set containing vertices as elements, the same B vertices will hit all created sets for hitting set. Okay, so if a solution to vertex cover of size B does not exist, then because we have created an equivalent, this is the equivalency type transformation, mapping of edges to sets and vertices to elements of those sets, a solution for hitting set could not possibly exist since it would require B elements vertices to cover all sets edges, which could only be possible as vertex cover had a solution. So we're taking a problem and we're mapping it one-to-one as a equivalency problem, and then we're saying if one has an answer, then the other has an answer. If one doesn't have an answer, the other one doesn't have an answer. And that's why hitting set, you can reduce vertex cover to hitting set. If you are trying to get a visualization of it, we're basically saying that given some graph, we're looking for some set of edges, so some set of vertices. Those are covered. That would cover all my edges. Okay, so now I need at least one more vertex to cover. Let's go with this one. Okay, so that's my vertex cover of covering all the edges, and so you are looking for this, some number of vertices, and similarly, you're looking for some hitting set that covers or hits all of your sets, which is represented as which is representing edges. So they're two equivalent problems. Okay. Questions about hitting sets?
So there's a question in the chat that says, is there some problem covered in DPV or in the lectures that hitting set is similar to? Like, is set cover related?
Set cover is related, but set cover is not one of your black boxes. It's not covered as a reduction in the lectures or in the book. I think it's mentioned, but I think it's because we don't actually have a full reduction in the lectures or in the book, it is not allowed. And the question is there some problem covering DPV that hitting set is similar to vertex cover, right? I did the reduction to vertex cover. Therefore, they're similar in the ideas that you're getting some set of items that cover a bunch of different sets. So they're very well related, which is why the reduction here works. Okay. Cool. All right, last problem. Hopefully. Definitely last problem. All right. Famous kite problem. A kite is a graph on an even number of vertices, say 2n, in which n of the vertices form a clique and the remaining n vertices are connected in a tail that consists of a path joined to one of the vertices of the clique. Given a graph And a goal G, the kite problem asks for a subgraph, which is a kite and with containing 2 G nodes. Prove that kite is NP complete. Notice that the solution to kite is specifically not defined as a set of vertices to form an induced subgraph, as with click and other problems. Okay, so there is a, you need to understand what an induced subgraph is and why this is not an induced subgraph. I know this is like a terrible timing of such a thing, but it matters. And this is, I think, the first problem that really addresses it. An induced subgraph, and I believe in the PDF, this is a link, is that you are given a set of vertices. So you're not given edges and you're given a set of vertices. When you induce a subgraph from that set of vertices, you are taking a look at the original graph that the vertices are from, and any edge between those set of vertices that exists in the original graph